Close your eyes, breathe slowly. Tonight we travel to the oldest science, to the first moment a human being looked up at the night sky and understood that what they were seeing was not chaos but pattern, not noise but language, not the random scattering of cold fire across an indifferent darkness but a clock, a calendar, a map, and a story, written in light across the ceiling of the world. Every civilization that has ever existed has looked up at these same stars. Every culture in the entire span of human history has named them, tracked them, feared them, worshipped them, and used them to organize the specific rhythms of planting and sailing and praying and dying that constitute the texture of a human life. The stars have been the oldest constant in the human experience, present before the first city was built, before the first word was written, before the first god was named. This is the story of the people who first learned to read them. This is explored during sleeping. Fact 1. The first astronomers, before there were words for what they did. History of astronomy, the systematic observation and interpretation of the sky, does not begin with the ancient Greeks, nor with the astronomers of Babylon, nor with the pyramid builders of Egypt, but in a period so remote that it predates writing, predates agriculture, and predates the first permanent human settlements by tens of thousands of years, in the specific activities of prehistoric human communities whose careful, sustained attention to the movements of the sun, the moon, the planets, and the stars constitutes the earliest expression of the scientific impulse in the entire human record. The evidence for prehistoric astronomical knowledge is preserved not in written texts. There were none, but in the specific orientation of monuments, in the alignment of grave, in the markings on bone and stone that record lunar cycles with a precision that required sustained, systematic observation over many months and years, and in the specific placement of ritual and funerary structures, whose alignment with the rising and setting points of the sun at the solstices and equinoxes could not be accidental, and can only be explained as the deliberate expression of an astronomical knowledge, whose specific character and cultural meaning we can partially reconstruct but never fully recover. The oldest potential astronomical artifact in the human record is the Lebombo bone, a baboon fibula discovered in the Lebombo Mountains on the border between South Africa and Swaziland, dated to approximately 43,000 years ago, and bearing 29 notches whose specific number corresponds to the length of the lunar month, with a precision that suggests deliberate lunar counting rather than random marking. If the interpretation is correct, and it is debated, as all interpretations of prehistoric artifacts necessarily are, then the Lebombo bone represents the first known attempt by a human being to impose numerical order on the movements of the sky, a moment of intellectual ambition whose specific consequences, extended across 43,000 years of subsequent development, produced every observatory, every telescope, every space mission, and every cosmological theory that the human species has subsequently created. The specific impulse that produced those 29 notches, the drive to count, to measure, to find the pattern beneath the apparent randomness, to make the sky legible, is the same impulse that produced modern astrophysics. It is one of the oldest things about us. Fact 2. Stonehenge, the calendar in stone. Stonehenge, the prehistoric monument on Salisbury Plain in Wiltshire, England, whose massive sarsen and bluestone uprights and lintels, arranged in concentric circles and horseshoe settings on a site that had been used for ritual purposes since approximately 3000 BCE, have been studied, debated, and wondered at by every generation since its construction, and whose specific astronomical alignments, above all the precise orientation of its main axis toward the rising sun at the summer solstice and the setting sun at the winter solstice, make it one of the most thoroughly discussed examples of prehistoric astronomical knowledge in the world, is not, as the popular imagination sometimes frames it, a mysterious anomaly in the prehistoric landscape, a monument whose purpose is entirely unknown and whose construction is inexplicable, but rather the most famous representative of a widespread tradition of megalithic monument construction in Neolithic and Bronze Age Europe, whose specific character, the consistent incorporation of solar and lunar alignments into the design and orientation of large stone structures, demonstrates that the systematic observation of the sky was a fundamental component of the religious, agricultural, and social life of prehistoric European communities across a period of more than 2,000 years. The specific astronomical alignments of Stonehenge are real, precisely established by modern survey, and cannot be explained as coincidence. The main axis of the monument is aligned within a fraction of a degree of the midsummer sunrise direction, as it would have appeared from the center of the monument at the time of its construction, and the same axis points toward the midwinter sunset, the specific moment in the annual solar cycle when the days stop shortening and the sun begins its return. An event of enormous practical and symbolic significance for agricultural communities whose survival depended on the accurate prediction of the seasons. The specific effort required to construct Stonehenge, the transportation of the bluestones from the Preseli Hills in Wales, approximately 250 kilometres away, the quarrying and erection of the enormous sarsen stones from Marlborough Downs. The sustained social organisation required to coordinate the labour of hundreds of people over generations was justified, in the specific worldview of its builders, by the specific importance of the astronomical knowledge the monument embodied, and the specific ritual functions it served in relation to the solar and lunar cycles it was designed to mark. Fact 3. The Babylonians, the first mathematical astronomers. The astronomers of ancient Babylon, the scholars who worked in the great cities of Mesopotamia, above all in Babylon itself, between approximately 850 BCE, maintaining the long-running observational records called the astronomical diaries, in which the nightly positions of the moon, the planets, and selected stars were recorded in cuneiform on clay tablets alongside meteorological observations, commodity prices, and political events. Were the first people in the documented history of science to develop a genuinely mathematical approach to the prediction of astronomical phenomena, creating the specific computational techniques whose accuracy and sophistication surpassed anything achieved in any other ancient civilization, and whose specific legacy, transmitted through Greek and then Islamic astronomy, forms one of the foundational threads of the modern astronomical tradition. The Babylonian Astronomical Diaries, a collection of observational records maintained with extraordinary consistency over a period of approximately 5 centuries, the longest continuous series of systematic scientific observations in the pre-modern world, provided the empirical foundation on which the mathematical astronomy of the later Babylonian period was built. From the accumulated data of these observations, Babylonian scholars identified the specific numerical patterns, the periods of the planetary cycles, the intervals between eclipses, the relationships between the lunar month and the solar year that allowed them to construct predictive algorithms of remarkable accuracy. The Saros cycle, the period of approximately 18 years, 11 days, and 8 hours after which the specific geometry of the Earth, Moon, and Sun repeats with sufficient precision to produce an almost identical sequence of eclipses, was identified by Babylonian astronomers from their accumulated eclipse records, and used to predict the occurrence of future eclipses with an accuracy that astonished the Greek scholars who encountered Babylonian astronomical knowledge in the Hellenistic period, and that remains, as a purely empirical achievement based on pattern recognition rather than physical understanding, one of the most impressive examples of astronomical observation in the ancient world. Fact 4. The Egyptian sky, stars, gods, and the Nile. The astronomical knowledge of ancient Egypt, the specific understanding of the sky that Egyptian civilization developed over 3,000 years of continuous cultural activity, expressed in the orientation of temples and pyramids, in the design of the religious calendar. In the specific mythology that identified the stars with gods and the movements of the heavens with the unfolding of divine drama, and in the practical astronomical observations that served the specific needs of a civilization whose entire agricultural system depended on the predictable annual flooding of the Nile, was not, in the modern sense, a science separate from religion, but rather an inseparable dimension of the specific Egyptian understanding of the cosmos, in which the movements of the sun, the moon, the stars, and the planets were simultaneously natural phenomena, divine actions, and the expressions of a cosmic order whose maintenance was the specific responsibility of the pharaoh and the priestly establishment. The most astronomically significant Egyptian achievement was the development of a calendar system based on the heliacal rising of the star Sirius, the specific moment each year when Sirius, after a period of invisibility due to its proximity to the sun, reappears on the eastern horizon just before sunrise. Its reappearance in the sky of ancient Egypt, occurring at approximately the same time as the beginning of the annual Nile flood that deposited the fertile silt on which Egyptian agriculture depended. The Egyptians identified this star as Sopdet, the goddess of the flood and the new year, and the heliacal rising of Sirius marked for them the beginning of the new year and the expected onset of the inundation, creating a specific connection between the astronomical calendar and the agricultural cycle, whose accuracy was confirmed year after year by the observed coincidence of the stellar and hydrological events it predicted. The specific precision required to identify and consistently observe the heliacal rising of Sirius, an event visible only in the specific window of days, when the star rises just far enough from the sun to be visible before the sky brightens, demonstrates an organized, sustained program of astronomical observation whose specific institutional context, the Egyptian temple system whose priests were responsible for the maintenance of the calendar. made it the first fully institutionalized astronomical program in the historical record. Fact 5. The Greek Revolution, from myth to mechanism. The specific transformation of astronomy from a primarily observational and mythological discipline, concerned with identifying patterns in the sky, naming the stars and constellations, and using astronomical cycles to organize the calendar and the religious year, into a theoretical science whose goal was the construction of geometrical models capable of explaining and predicting the observed motions of the celestial bodies in terms of underlying physical or mathematical principles. Represents one of the most consequential intellectual revolutions in the entire history of human thought, and it occurred in the Greek-speaking world of the 6th to 3rd centuries BCE with a speed and a thoroughness that has no precedent in the intellectual history of any other civilization. The specific character of the Greek astronomical revolution was the application to the sky of the geometrical thinking that Greek mathematicians were simultaneously developing in other domains. The specific insight that the observed motions of the celestial bodies, complex and irregular as they appeared, could be analyzed as the combined result of simpler, more regular motions whose specific parameters could be determined from observation, and whose combination could reproduce the observed phenomena with mathematical precision. The first step in this direction was the proposal, attributed to the Pythagorean tradition of the 6th and 5th centuries BCE, that the Earth was a sphere, a conclusion reached not from direct observation of the Earth's curvature, but from the geometrical elegance of the sphere as a form, from the observation that the Earth casts a circular shadow on the Moon during lunar eclipses regardless of the orientation of the shadow, and from the specific observation that the altitude of the stars changes as one travels north or south, consistent with a spherical Earth and inconsistent with a flat one. From this foundational insight, Greek astronomers proceeded, over the following 3 centuries, to determine the size of the Earth, to propose the first heliocentric model of the solar system, to measure the distance to the Moon, and to construct the first comprehensive geometrical model of the motions of the Sun, Moon, and planets, achievements whose specific intellectual character places them, despite their occurrence more than 2,000 years ago, recognizably within the same tradition of mathematical natural science that produced modern astronomy. Fact 6. Eratosthenes, measuring the Earth with a shadow. The measurement of the circumference of the Earth by the Alexandrian scholar Eratosthenes of Cyrene in approximately 240 BCE, an achievement accomplished not with any instrument more sophisticated than a stick, a well, and the specific geometrical reasoning that the Greek intellectual tradition had made available to him, and producing a result accurate to within a few percent of the modern value, is one of the most celebrated and most frequently cited examples of ancient scientific reasoning, and one whose specific method is so elegant, so simple in its fundamental principle, and so powerful in its application that it remains, after more than 2,000 years, one of the clearest demonstrations available of what careful observation combined with rigorous geometrical thinking can achieve. Eratosthenes knew, from reports available in the Great Library of Alexandria, of which he was the chief librarian, that at noon on the summer solstice, the sun shone directly down a well in the city of Sin, modern Aswan in southern Egypt, without casting any shadow on the well's walls, indicating that the sun was directly overhead at that location on that day. In Alexandria, approximately 800 kilometers to the north of Sin, he observed that at the same moment on the same day, a vertical stick cast a shadow whose angle from the vertical was approximately 1/50th of a full circle, approximately 7.2 degrees. The geometrical reasoning required to convert these two observations into a measurement of the Earth's circumference was straightforward. If the sun is sufficiently far away that its rays are effectively parallel, then the difference in the shadow angle between the two locations must equal the angle subtended at the Earth's center by the arc between them, meaning that the arc from Alexandria to Sin represents 1/50th of the Earth's full circumference. Multiplying the distance between the two cities by 50 gave Eratosthenes a circumference of approximately 252,000 stadia, a value whose conversion to modern units depends on the specific length of the stadium he used, but which most historians of science estimate as falling between 39,000 and 46,000 kilometers, compared to the modern value of approximately 40,075 kilometers for the Earth's equatorial circumference. The specific intellectual achievement represented by this measurement is not merely its accuracy, but its method, the demonstration that the size of the entire Earth could be determined by a scholar sitting in a library, reasoning from two shadow measurements and a geometrical principle, without leaving Alexandria. Fact 7. Aristarchus, the ancient astronomer who knew the Earth moved. Aristarchus of Samos, the Greek astronomer who worked in Alexandria in the early 3rd century BCE and who proposed, approximately 18 centuries before Copernicus, published the heliocentric model that is conventionally described as the beginning of the Copernican revolution, that the Sun rather than the Earth was at the center of the cosmos, that the Earth rotated on its own axis once per day, and that the apparent annual motion of the Sun against the background of the stars was the result of the Earth's annual orbit around the Sun, is one of the most intellectually remarkable figures in the entire history of astronomy, and one whose specific achievement, the correct identification of the basic structure of the solar system from pure geometrical reasoning applied to observational data, has been consistently underappreciated in the popular history of science because the model he proposed was rejected by the subsequent Greek astronomical tradition and did not enter the mainstream of astronomical thinking until Copernicus, working independently, arrived at the same conclusion nearly 2 millennia later. The specific reasoning that led Aristarchus to the heliocentric conclusion began with a geometrical method for estimating the relative distances of the Sun and Moon from the Earth, based on the observation of the angle between the Sun and the half-moon, when the Moon is exactly half illuminated as seen from the Earth. The angle at the Moon between the Earth and the Sun is exactly 90 degrees, meaning that the Earth, Moon, and Sun form a right triangle whose dimensions can be calculated if the angle at the Earth between the Moon and the Sun can be measured. Aristarchus measured this angle as approximately 87 degrees, giving him a ratio of Sun-to-Moon distance of approximately 19:1, a significant underestimate of the true ratio of approximately 390:1 due to the extreme difficulty of identifying the precise moment of half-illumination, but sufficient to establish that the Sun was very much farther from the Earth than the Moon and therefore, given its apparently similar angular size in the sky, very much larger. The specific conclusion Aristarchus drew from this reasoning, that it was more physically reasonable for the smaller body to orbit the larger than vice versa, was the intellectual step that led him to place the Sun at the center of the cosmos. Fact 8. The Antikythera mechanism, an ancient computer. The Antikythera mechanism, the fragmentary bronze device recovered in 1901 from a Roman-era shipwreck discovered by sponge divers near the Greek island of Antikythera, dated to approximately 60 to 150 BCE, and subsequently revealed by more than a century of increasingly sophisticated analysis to be a hand-powered mechanical computer of extraordinary complexity, capable of calculating and displaying the positions of the Sun and Moon in the sky, the phase of the Moon, the timing of solar and lunar eclipses, the dates of major Pan-Hellenic athletic games including the Olympic Games, and the positions of the 5 planets known to the ancient world, is the most sophisticated mechanical artifact to survive from the ancient world, and one whose specific existence has fundamentally revised the understanding of the technological capabilities of ancient Greek civilization. The mechanism's complexity, approximately 30 interlocking bronze gears of varying sizes and tooth counts, arranged within a wooden case approximately the size of a shoebox, with dials and inscriptions on both front and back faces, whose specific content has been partially reconstructed from the surviving fragments, was not suspected from the corroded, encrusted fragments recovered from the shipwreck until X-ray imaging in the 1970s and high-resolution computed tomography scanning in the 21st century revealed the gear trains and inscriptions preserved within the corrosion. The specific astronomical computations performed by the mechanism are implemented through a series of gear trains whose tooth ratios encode the specific numerical relationships between the periods of the celestial bodies being tracked: the 19-year Metonic cycle, the 18-year Saros eclipse cycle, the 76-year Callippic cycle. With a mechanical precision that required the ability to cut gears of specific tooth counts to tolerances achievable only by craftsmen of exceptional skill, working with tools of high quality. The existence of the Antikythera mechanism raises a question that has not been fully answered. If ancient Greek craftsmen were capable of building a device of this sophistication, why is there no other evidence of comparable mechanical complexity in the surviving record of ancient technology? And what other achievements of ancient Greek engineering have been entirely lost to the specific accidents of preservation that have delivered this single extraordinary object to the modern world? Fact 9. Babylonian star catalogues, the first map of the sky. The systematic cataloguing of the stars, the identification, naming, and positional recording of the individual stars visible to the naked eye in sufficient number, and with sufficient precision to constitute a reference map of the sky, was accomplished first not by the Greeks, as the popular history of astronomy sometimes implies, but by the astronomers of Mesopotamia, whose cuneiform star catalogues, Compiled over a period of centuries and preserved on clay tablets that have survived to the present in the collections of major museums, represent the oldest systematic maps of the sky in the historical record and the specific foundation on which every subsequent stellar catalogue, from Hipparchus through Ptolemy to the modern Hipparcos satellite survey, has built. The oldest substantial Babylonian star catalogue is the Mulapin, named for its opening words, which translate as the plough star, referring to the constellation we call Triangulum, a compilation whose surviving copies date to approximately 700 BCE, but which appears to have been composed from observational records considerably older, possibly as early as 1200 BCE. The Mulapin catalogues approximately 70 constellations and individual stars, organized into three paths across the sky: the path of Enlil in the north, the path of Anu in the equatorial zone, and the path of E in the south, and provides specific information about the heliacal risings and settings of each star, the intervals between the risings of successive stars, and the relationships between stellar events and the agricultural calendar. The specific constellations identified in the Mulapin, many of which are recognizable as the ancestors of the modern Western constellations, including versions of Orion, Leo, Scorpius, and the 12 constellations of the zodiac, represent the oldest surviving layer of the Western astronomical tradition. A specific inheritance from Babylonian skywatchers that passed through Greek and Islamic astronomy into the modern star maps that any amateur astronomer uses today when they look up at a winter sky and find Orion by his belt. Fact 10. Ancient astronomy at 10. The sky as the first science. 10 facts into the story of ancient astronomy, and the arc of what we are tracing has already become clear. This is not merely a history of technical knowledge accumulating from one civilization to the next, but a history of the specific human relationship with the night sky, the oldest and most universal relationship between our species and the cosmos we inhabit, expressed in 43,000-year-old bone notches and in the precise gear trains of a bronze computer recovered from the bottom of the Aegean Sea. We have stood at Stonehenge at midsummer and understood that the people who built it were not primitive mystics, but careful observers of the solar cycle, whose specific knowledge of the sky was precise enough to orient a monument of that scale to within a fraction of a degree of the solstice sunrise. We have sat with Babylonian scholars in the temples of Mesopotamia and watched them maintain the oldest continuous scientific observational record in history, identifying in the accumulated data of 5 centuries the specific numerical patterns that would allow them to predict the future of the sky. We have followed Eratosthenes as he measured the circumference of the entire Earth with a stick and a shadow, and stood with Aristarchus as he looked at the geometry of the solar system and understood, 18 centuries before Copernicus, that the Earth was moving. 90 facts remain. They will carry us through the astronomical traditions of every major civilization on Earth: Chinese, Indian, Islamic, Mayan, Polynesian, through the specific instruments and the specific discoveries that transformed the human understanding of the cosmos from mythology to mathematics, and through the deep question that has animated every astronomer who has ever worked, from the first human who noticed that the stars rose and set in predictable patterns to the last. What is it that we are actually looking at when we look up at the night sky? This is explored during sleeping. Fact 11. Hipparchus, the father of observational astronomy. Hipparchus of Nicaea, the Greek astronomer who worked primarily on the island of Rhodes in the 2nd century BCE, approximately between 190 and 120 BCE, and whose specific contributions to observational and mathematical astronomy were so numerous, so fundamental, and so precisely executed that the historian of science Otto Neugebauer described him as the greatest astronomical observer of antiquity, and whose work provided the empirical and mathematical foundation on which Ptolemy built the geocentric model that dominated Western and Islamic astronomy for 14 centuries, is the most consequential figure in the history of ancient Greek astronomy, and one whose specific achievements, reconstructed painstakingly from the surviving fragments of his own work and from the extensive citations and critiques in Ptolemy's Almagest, reveal a scientist of exceptional rigor, exceptional observational skill, and exceptional intellectual honesty, whose specific willingness to acknowledge the limitations of existing models and to demand that theory match observation to the highest achievable standard define the specific character of the Greek astronomical tradition at its best. Among Hipparchus's most celebrated achievements was the discovery of the precession of the equinoxes, the slow westward drift of the equinoctial points against the background of the fixed stars, produced by the slow wobble of the Earth's rotational axis over a cycle of approximately 26,000 years, which Hipparchus identified by comparing his own measurements of the positions of fixed stars with the measurements recorded by earlier Babylonian observers. finding that the positions of the stars had shifted by approximately 2 degrees in the approximately 150 years, separating his observations from the earlier ones. The specific intellectual achievement represented by this discovery, the identification, from measurements separated by a century and a half, of a motion so slow that it shifts the stellar positions by only about 1 degree every 72 years, required both the extraordinary precision of Hipparchus's own observations and the specific availability of the earlier Babylonian records, whose quality was sufficient to make the comparison meaningful, and demonstrates with particular clarity the specific value of long-term observational records in astronomy, a value that Hipparchus understood with exceptional depth. Fact 12. The Zodiac, 12 Signs, One Ancient Sky. The zodiac, the band of 12 constellations, through which the sun appears to move over the course of a year as the Earth orbits around it, and whose specific division into 12 equal sectors of 30 degrees each sector named for the constellation originally associated with it, constitutes one of the oldest and most enduring frameworks in the entire history of human engagement with the sky. Was developed in its fully systematic form by the astronomers of Babylonia in approximately the 5th century BCE. Building on an older tradition of celestial observation and omen interpretation that had been accumulating in Mesopotamia for more than 1,000 years, and whose specific character combined the practical astronomical purpose of providing a coordinate system for recording and predicting the positions of the moon and planets with the astrological purpose of interpreting those positions as omens relevant to the welfare of the king and the state. The specific astronomical function of the zodiac was to provide a reference framework for the description of planetary positions, a way of saying where in the sky a planet was located by specifying which zodiacal sign it occupied and how many degrees into that sign it had progressed. The 12 signs of the Babylonian zodiac were defined as equal 30-degree sectors of the ecliptic, the apparent annual path of the sun against the background stars, regardless of the actual sizes of the constellations associated with them, creating a mathematical framework whose specific regularity made it ideal for the computational astronomy that the Babylonians were developing. The Babylonian zodiac passed into Greek astronomy in the 4th century BCE, where it was adopted and refined by the Greek mathematical tradition, and from Greek astronomy into the Roman, Islamic, and eventually the modern Western astrological and astronomical traditions, whose continued use of the same 12 zodiacal signs, Aries, Taurus, Gemini, Cancer, Leo, Virgo, Libra, Scorpio, Sagittarius, Capricorn, Aquarius, Pisces, after more than 2,500 years, represents one of the most remarkable continuities in the entire intellectual history of human civilization. Fact 13. Chinese astronomy, the sky as imperial mandate. The astronomical tradition of ancient China, the system of sky observation, record-keeping, calendar calculation, and celestial interpretation that was maintained, with extraordinary continuity, by the official astronomical bureaus of successive Chinese dynasties from at least the Shang dynasty of the 2nd millennium BCE through the Qing dynasty that ended in 1912 CE. A span of more than 3,000 years that makes it the longest continuous institutional astronomical tradition in the history of any civilization, was shaped from its earliest period by a specific cosmological and political framework whose particular character distinguished it profoundly from the astronomical traditions of Babylon, Greece, and the Islamic world. The understanding of the sky as the domain of the Emperor of Heaven, whose specific relationship with the Emperor of China was expressed in the celestial events that the imperial astronomers observed, interpreted, and reported to the throne. The specific institutional context of Chinese astronomy, the organization of astronomical observation as an imperial function, performed by official astronomers whose duty was to maintain the calendar, observe and interpret celestial omens, and report anomalous celestial phenomena to the emperor, produced a tradition of observational record-keeping whose specific scope and duration are unmatched in the history of any other civilization. The Chinese imperial astronomical records contain the oldest surviving accounts of sunspot observation. The naked-eye observation of sunspots through thin cloud or haze was apparently a regular practice of Chinese astronomers from at least the 2nd century BCE, producing a record of solar activity extending far beyond the period covered by European telescopic observation. The Chinese records contain the most comprehensive historical catalogue of cometary appearances, including the specific observational records of Halley's Comet that allow its orbital history to be traced back to at least 240 BCE, more than 2 millennia before Edmund Halley identified the periodicity of the comet that bears his name. and the specific record of the supernova of 1054 CE, the stellar explosion whose remnant is now observed as the Crab Nebula, is preserved in Chinese, Japanese, and Arab records, but not in European ones, reflecting the specific difference in observational culture between a tradition that maintained continuous systematic sky observation as an institutional obligation, and one that, in the medieval European case, had no comparable institutional structure for the regular monitoring and recording of the sky. Fact 14. The Maya calendar, the most sophisticated timekeeping in the ancient Americas. The astronomical knowledge of the ancient Maya, the Mesoamerican civilization that flourished in the lowlands and highlands of modern Mexico, Guatemala, Belize, Honduras, and El Salvador between approximately 2000 BCE and the Spanish conquest of the 16th century CE, and whose specific astronomical achievements, embedded in a calendrical and mathematical system of extraordinary sophistication, represent the most advanced astronomical tradition developed independently in the ancient Americas, was not, as the popular imagination sometimes presents it, primarily a system of prophecy or apocalyptic prediction, but a practical, precise, and mathematically refined body of knowledge about the motions of the sun, moon, planets, and stars, whose specific applications encompass the organization of the agricultural cycle, the scheduling of religious ceremonies, the recording of historical events, and the coordination of political activity across the dispersed communities of the Maya world. The Maya calendrical system was built on the intersection of two independent cycles: the 365-day solar calendar called the Harb, organized into 18 months of 20 days plus 5 additional days, and the 260-day ritual calendar called the Tzolk'in, whose specific origin is debated, but whose period corresponds to neither the solar year nor the lunar month, and may be related to the length of human gestation, or to the period of visibility of Venus as a morning or evening star in the latitude of the Maya heartland. The combination of these two cycles, the calendar round, produced a period of 18,980 days, approximately 52 years, before the same day name in both calendars coincided again, creating a cycle of sufficient length to serve as the primary chronological framework for historical recording in the Maya world. The specific Venus tables of the Dresden Codex, one of the 4 surviving pre-Columbian Maya books, record the synodic period of Venus with an accuracy of approximately 1 day in 500 years, an achievement that required sustained, systematic observation of Venus's appearances as morning and evening star over a period of many decades, and the specific mathematical skill to extract the underlying period from the observed data. Fact 15. Islamic Golden Age Astronomy, preserving and advancing the ancient knowledge. The astronomers of the Islamic Golden Age, the scholars working in the great intellectual centers of Baghdad, Cairo, Samarkand, Cordoba, and other cities of the Islamic world between approximately the 8th and 15th centuries CE, in the period when Islamic civilization was the most scientifically productive in the world, played a role in the history of astronomy that is simultaneously one of the most consequential and one of the most consistently underappreciated in the popular understanding of how modern science came to be. They preserved the Greek astronomical tradition at a time when it was in danger of being lost to the Latin West, translated the key texts of Greek astronomy into Arabic and thereby ensured their survival, and then, critically, went far beyond preservation to make specific, substantial, and enduring contributions to observational theoretical and instrumental astronomy, whose specific character represents not merely the maintenance of an inherited tradition, but its active advancement. The translation movement of the 8th and 9th centuries, the systematic effort, sponsored by the Abbasid caliphs of Baghdad, and centered above all on the great translation center of the House of Wisdom, to render the major works of Greek science into Arabic, brought into Arabic the complete works of Ptolemy, Euclid, and Aristotle, along with the astronomical traditions of India and Persia, creating in the libraries of the Islamic world the most comprehensive collection of scientific knowledge assembled anywhere on Earth up to that time. The specific name by which Ptolemy's great astronomical treatise is known today, the Almagest, is itself a testimony to the Arabic transmission. The title is a corruption of the Arabic Al-Majisti, meaning the greatest, the name given by Arabic translators to a work they recognized as the supreme achievement of ancient mathematical astronomy. Islamic astronomers then proceeded to test Ptolemy's models against new observations, made with instruments of greater precision than any available in the ancient world, identifying specific discrepancies between the Ptolemaic predictions and the observed positions of celestial bodies that accumulated over several centuries into a body of evidence whose resolution would eventually require not the refinement of the Ptolemaic system, but its replacement. Fact 16. Ptolemy and the Almagest, the book that ruled the sky for 14 centuries. The Almagest, the comprehensive mathematical treatise on astronomy, written by Claudius Ptolemy of Alexandria in approximately 150 CE, whose full Greek title Mathematic Syntaxis, the mathematical compilation, was later superseded by the honorific Megis Syntaxis, the greatest compilation, from which the Arabic Almagisti and the modern name Almagest derive, is the most influential astronomical work ever written. The book that defined the framework within which Western and Islamic astronomers understood the motions of the sky for 1400 years, and whose specific content, a complete mathematical theory of the motions of the Sun, Moon, and 5 planets, implemented through a system of geometrical models whose parameters were derived from observations and whose predictions matched those observations to the accuracy achievable by naked eye measurement, represents the culmination of the entire tradition of Greek mathematical astronomy and one of the greatest achievements of ancient science. The geocentric model presented in the Almagest, the model in which the Earth stands motionless at the center of the cosmos, surrounded by the crystalline spheres carrying the Moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn in order of increasing distance, the whole enclosed by the sphere of the fixed stars, was not, as it is sometimes portrayed, a simple or naive picture of the cosmos, but a sophisticated mathematical construction whose specific devices, the deferent and epicycle, the eccentric and above all the equant, the specific geometrical innovation that allowed the model to reproduce the non-uniform apparent motions of the planets with sufficient accuracy to be practically useful, represented the solution, within the constraints of circular motion that Greek astronomical tradition required, to one of the hardest mathematical problems that ancient science had confronted. The Almagest's dominance of astronomical thinking for 14 centuries was not the product of intellectual conservatism or the suppression of alternatives. It endured because it worked, because its predictions of planetary positions, while not perfect, were accurate enough for the practical purposes of calendar making, navigation, and astrology that constituted the primary applications of astronomy in the ancient and medieval world. And because no alternative model of comparable mathematical completeness and predictive power was available until Copernicus constructed one in the 16th century. Fact 17. Indian Astronomy, Mathematics in Service of the Stars. The astronomical tradition of ancient India, the systematic body of sky knowledge, developed in the Indian subcontinent from at least the Vedic period of the 2nd millennium BCE, expressed in the astronomical sections of the Vedas, in the Jyotisha Vedanga treatises on calendar computation, and above all in the great mathematical astronomical texts called the Siddhantas. Produced between approximately the 4th and 7th centuries CE by a succession of brilliant mathematicians and astronomers whose specific contributions to both astronomy and mathematics place them among the most gifted scientists of the ancient world, was shaped by the same fundamental concerns that drove astronomical development in every other ancient civilization. The accurate determination of the calendar for ritual purposes, the prediction of eclipses and planetary positions, and the theoretical understanding of the motions of the celestial bodies. The specific mathematical achievements of the Indian astronomical tradition are inseparable from the development of the numerical system, the decimal positional notation, with a symbol for 0, that Indian mathematicians created and that the Islamic world transmitted to Europe as the Hindu-Arabic numeral system, the foundation of all modern computational mathematics. The greatest figure of the classical Indian astronomical tradition is Aryabhata, the mathematician and astronomer who was born in 476 CE and whose text, the Aryabhatiya, written in 499 CE when its author was 23 years old, contains a summary of the mathematical and astronomical knowledge of his time that includes the specific proposal that the Earth rotates on its own axis once per day, producing the apparent daily rotation of the sky, rather than the sky itself rotating around a stationary Earth, a heliocentric or geokinetic insight whose specific expression in the Aryabhatiya predates by more than a millennium the Copernican revolution conventionally associated with the beginning of the modern astronomical worldview. Aryabhata also calculated the length of the sidereal year, the time for the Earth to complete one orbit of the Sun relative to the fixed stars, as 365 days, 6 hours, 12 minutes and 30 seconds, a value that differs from the modern measurement by only 3 minutes and 20 seconds, an accuracy remarkable for any period of astronomical history. Fact 18. Stonehenge's companions, megalithic astronomy across Europe. The specific tradition of incorporating solar and lunar alignments into the design of large stone monuments, the practice whose most famous expression is Stonehenge, but whose actual geographic distribution extends across virtually the entire Atlantic facade of prehistoric Europe, from the stone circles of Orkney in northern Scotland, through the megalithic tombs of Ireland, Wales, Brittany, and the Iberian Peninsula to the temples of prehistoric Malta, represents one of the most widespread and most persistent expressions of astronomical knowledge in the prehistoric world, demonstrating that the systematic observation of the sun and moon, and the specific use of that observation to orient significant structures, was a fundamental component of Neolithic and Bronze Age European culture across a period of more than 2,000 years and a geographic range of more than 3,000 kilometers. The Passage Tomb of Newgrange in the Boyne Valley of Ireland, constructed approximately 3200 BCE, making it approximately 500 years older than Stonehenge, is perhaps the most dramatic single example of prehistoric solar alignment anywhere in Europe. A large circular mound containing a long stone passage leading to a central chamber, whose specific orientation is aligned so precisely with the midwinter sunrise that on the mornings of the winter solstice, and for approximately 5 days on either side of it, the rising sun shines directly down the passage and illuminates the central chamber with a shaft of golden light for approximately 17 minutes. The specific engineering required to achieve this alignment, the construction of a stone passage approximately 19 meters long, whose floor rises gradually from the entrance to the chamber, topped by a specially constructed roof box above the entrance whose specific purpose was to admit the low winter solstice sun while excluding the higher summer sun, demonstrates an astronomical knowledge and a constructional precision that transforms the simple observation of the solstice sunrise into a specific architectural experience of extraordinary power, one that was clearly designed to produce in the people who witnessed it a specific emotional and spiritual response to the specific astronomical event it marked. Fact 19. The Polynesian navigators reading the sky to cross the Pacific. The navigational astronomy of the Polynesian peoples, the specific body of sky knowledge, transmitted across generations through oral tradition, practical apprenticeship, and the accumulated experience of voyaging across the largest ocean on Earth, that allowed Polynesian navigators to sail from island to island across the Pacific in double-hulled canoes without instruments, charts, or compasses, using the stars, the sun, the moon, the ocean swells, the winds, the birds, and the specific behavior of the sea itself as their navigational guides, represents one of the most remarkable practical applications of astronomical knowledge in the entire history of human engagement with the sky, and one whose specific achievement, the settlement of virtually every habitable island in the Pacific, including Hawaii, New Zealand, and Easter Island, by approximately 1000 CE, remains. When its full geographic scope and its specific technical demands are properly understood, among the greatest feats of navigation in human history. The core of Polynesian celestial navigation was the star compass, the conceptual framework in which the horizon was divided into approximately 32 named sectors, each one defined by the rising or setting position of a specific star or constellation, and which provided the navigator with a mental map of the sky, whose specific stars served as directional guides for sailing towards specific island destinations. The navigator's knowledge encompassed not only the rising and setting positions of individual stars, but their culmination altitudes, the specific height above the horizon at which each star crossed the meridian, which corresponds to the latitude at which that star passes directly overhead, and which allowed Polynesian navigators to maintain a specific latitude by keeping a specific star at or near the zenith. The specific stars whose zenith passages mark the latitudes of the major Pacific island groups, Arcturus for Hawaii, the Southern Cross for various island groups in the South Pacific, were identified and incorporated into the navigational tradition as specific targets for voyages to those destinations, creating a specific astronomical map of the Pacific encoded in the rising, setting, and zenith points of the star compass that the navigator carried in memory rather than on paper. Fact 20. Ancient astronomy at 20. The sky without borders. 20 facts into the story of ancient astronomy, and the most important thing the story has already revealed is this: there was no civilization on Earth at any period of the human past that did not look up. The specific form that sky knowledge took, the mathematical tables of Babylon, the geometric models of Greece, the imperial omen archives of China, the interlocking calendar cycles of the Maya, the star compass of the Polynesian navigator, varied enormously with the specific needs, the specific intellectual frameworks, and the specific cultural priorities of the civilization that produced it. But the underlying impulse, the drive to find pattern in the sky, to use that pattern to organize time and space, to embed the specific movements of the celestial bodies in the stories and the meanings that made a culture's world coherent, was universal, present in every human civilization that the historical and archaeological record has recovered, and almost certainly in every human community that has ever existed. We have understood that the stars guided the ships of Polynesian navigators across the largest ocean on Earth before any European had found his way out of the Mediterranean. We have held the Antikythera mechanism and understood that a device of greater mechanical sophistication than anything Europe would build for another 1,000 years was constructed in the 2nd century BCE to track the motions of the sun, moon, and planets. We have followed Aristarchus to his heliocentric conclusion and understood that the revolution Copernicus is credited with had already been accomplished, in essence, 18 centuries before. 80 facts remain. They will carry us through the full breadth of the ancient astronomical world, through the observatories and the instruments, the specific discoveries and the specific people who made them, the specific myths that the sky inspired and the specific sciences it eventually became. The stars have been watching us for as long as we have been watching them. This is explored during sleeping. Fact 21. The astronomical ceiling of Senenmut, Egypt's oldest star map. The astronomical ceiling of the tomb of Senenmut, the powerful official who served as chief steward and architect to the female pharaoh Hatshepsut of the 18th dynasty, constructed in approximately 1473 BCE in the cliffs above the temple of Deir el-Bahari on the west bank of the Nile at Luxor, and whose burial chamber ceiling, painted in deep blue and golden yellow on a ground of astronomical significance, constitutes one of the oldest surviving visual representations of the night sky and of specific astronomical knowledge in the entire ancient Egyptian record, is a document of extraordinary interest for the history of Egyptian astronomy, both for the specific celestial content it depicts and for the specific questions it raises about the nature and purpose of astronomical knowledge in the context of the Egyptian funerary tradition. The ceiling is divided into two halves, the northern and southern, each presenting a different aspect of Egyptian astronomical knowledge. The northern half depicts the circumpolar constellations, the stars that in the latitude of ancient Egypt never set below the horizon, but circle continuously around the celestial North Pole, including the constellation of Meskhetiu, the bull's foreleg, which corresponds approximately to the modern constellation of Ursa Major, depicted as it was in the Egyptian astronomical tradition as the severed foreleg of a bull tethered by a rope to a mooring post at the North Celestial Pole. The southern half depicts the decans, the 36 star groups whose successive heliacal risings, spaced approximately 10 days apart, divided the Egyptian year into 36 weeks of 10 days each, and whose specific sequence, tracked through the year, provided Egyptian astronomers with a star clock capable of determining the hour of the night from the observation of which decan was rising on the eastern horizon. The specific astronomical content of the Senenmut ceiling represents a snapshot of Egyptian astronomical knowledge in the New Kingdom period whose specific details, the positions of the planets depicted on the ceiling, the specific decan sequence shown, have been used by modern scholars to attempt to determine the precise date of the ceiling's construction, in what constitutes one of the most ambitious applications of astronomical dating to an ancient Egyptian monument. Fact 22. The armillary sphere, modeling the cosmos in rings. The armillary sphere, the astronomical instrument consisting of a nested series of rings representing the principal circles of the celestial sphere, including the celestial equator, the ecliptic, the meridian, the horizon, and the colures, arranged concentrically around a central ball representing the Earth and capable of being set to the latitude of any observation site and rotated to represent the daily rotation of the sky, was one of the most important astronomical instruments of the ancient and medieval world, serving simultaneously as a model of the cosmos, a teaching tool for understanding the geometry of the celestial sphere, and in some of its more elaborate forms, a practical observing instrument for measuring the positions of celestial bodies. The armillary sphere was developed independently in both the Greek and the Chinese astronomical traditions, reflecting the specific utility of a three-dimensional model of the celestial sphere for teaching and understanding the specific geometric relationships between the various circles and points of the astronomical coordinate system. In the Greek tradition, the invention of the armillary sphere is attributed to various figures, including Eratosthenes and Hipparchus, and the instrument was used by Greek astronomers to demonstrate the specific geometric relationships between the celestial equator, the ecliptic, and the horizon that underlie the phenomena of the rising and setting of the sun and stars. In China, the development of the armillary sphere is documented from at least the 2nd century BCE, and successive Chinese dynasties invested enormous resources in the construction of increasingly elaborate armillary spheres for the Imperial Astronomical Bureau, the most sophisticated of which, the Great Bronze Armillary Sphere constructed for the Yuan dynasty in the 13th century CE by the astronomer Gu Shaojing, was an instrument of such precision and such mechanical complexity that it represented the pinnacle of pre-telescopic astronomical instrumentation anywhere in the world. Fact 23. The Mayan Dresden Codex, Astronomy, survived on bark paper. Dresden Codex, one of only 4 surviving books produced by the pre-Columbian Maya civilization, named for the city in whose library it has been held since its acquisition in the late 18th century, dating to approximately the 11th or 12th century CE, but believed to be a copy of a still older original, and consisting of 39 sheets of bark paper, folded accordion style into a book of 78 pages, covered in intricate painted hieroglyphic text and imagery, is one of the most important astronomical documents to survive from any ancient civilization, containing within its pages a series of mathematical tables whose specific content reveals the extraordinary precision and sophistication of Maya astronomical knowledge and whose specific survival, among the very few Maya books to escape the systematic destruction carried out by the Spanish bishop Diego de Landa in 1562, represents one of the great accidents of intellectual preservation in the history of human knowledge. The most astronomically significant content of the Dresden Codex is the Venus Table, a series of pages recording the synodic cycle of Venus, the planet whose specific behavior as the brightest object in the sky after the sun and moon, appearing alternately as the brilliant morning star in the east before sunrise and the evening star in the west after sunset, made it the most carefully tracked planet in Maya astronomy and the subject of a specific religious and astrological tradition whose particular intensity reflected the specific importance of Venus as a war deity in the Maya cosmological framework. The Venus Table tracks 5 complete Venus cycles, each of 584 days, the Maya average of the planet's actual synodic period of approximately 583.92 days, across a total period of 8 years, noting the specific dates of Venus's first appearance as morning star, its disappearance into superior conjunction with the Sun, its reappearance as evening star, and its disappearance into inferior conjunction, with a correction scheme that compensated for the small accumulated error of the 584-day average over long time periods, and maintained the table's accuracy across centuries of continued use. Fact 24. Al-Battani, the Islamic astronomer who corrected Ptolemy. Al-Battani, the Arab astronomer born in approximately 858 CE in Baton, in what is now Turkey, who worked as an observer and mathematician in the city of Raqqa on the Euphrates River in what is now northern Syria, and who produced in the course of approximately 40 years of systematic astronomical observation a body of work whose specific quality and accuracy surpassed anything achieved by his Greek predecessors, and established him as the greatest observational astronomer between Hipparchus in the 2nd century BCE and Tycho Brahe in the 16th century CE, represents the highest achievement of the Islamic astronomical tradition in the specific domain of precision measurement. His careful, sustained observations of the positions and motions of the Sun, Moon, and planets producing results that identified specific errors in Ptolemy's values and replaced them with measurements of superior accuracy. Al-Battani's most celebrated achievement was the precise determination of the length of the solar year and the specific parameters of the Sun's apparent motion, the eccentricity and the orientation of the solar orbit in the Ptolemaic framework from a long series of careful observations of the Sun's position throughout the year. His value for the length of the tropical year, the time from one vernal equinox to the next, the basis of the solar calendar, was 365 days, 5 hours, 46 minutes and 24 seconds, an error of only about 2 minutes and 22 seconds from the modern value, and significantly more accurate than Ptolemy's value, which was in error by approximately 6 minutes. Al-Battani also determined the specific value of the precession of the equinoxes, the slow westward drift of the equinoctial points first identified by Hipparchus, as approximately 1 degree in 66 years, compared to Hipparchus's value of 1 degree in 100 years, and the modern value of 1 degree in approximately 72 years. Demonstrating a precision of measurement that required both exceptional observational skill and the specific mathematical tools, whose development was one of Al-Battani's own contributions. He was one of the first astronomers to apply the specifically trigonometric functions of sine and cosine to astronomical calculations, replacing the chord tables of the Greek tradition with the more computationally convenient trigonometric notation that became standard in all subsequent mathematical astronomy. Fact 25. Göbekli Tepe and the oldest astronomical site, 12,000 years of sky. Göbekli Tepe, the remarkable archaeological site in southeastern Turkey, near the city of Şanlıurfa, excavated since 1994 by German and Turkish archaeologists, and dated to approximately 9600 to 8200 BCE, making it the oldest known example of large-scale monumental architecture anywhere on Earth, predating Stonehenge by approximately 6,000 years, and the construction of the Egyptian pyramids by approximately 5,000 years, has been proposed by several researchers on the basis of the specific orientations of its enclosures and the specific imagery carved on its massive T-shaped limestone pillars, as a site with significant astronomical dimensions whose particular character, if the interpretations are correct, would push the documented history of systematic astronomical observation and its incorporation into monumental architecture back into a period considerably older than any previously known example. The site consists of at least 20 circular or oval enclosures, each containing two large central T-shaped pillars surrounded by a ring of smaller T-pillars, set into stone benches that line the inner circumference of the enclosure wall. The specific orientations of the enclosures, the specific directions in which the central pillars face, and the specific astronomical events, the rising of particular stars, the positions of the sun at the solstices and equinoxes, that align with these orientations have been analyzed by researchers including the archaeoastronomer Juan Antonio Belmont and the independent researcher Andrew Collins, who have proposed specific astronomical alignments involving the rising of Deneb, the brightest star of the constellation Cygnus, at the horizon position toward which the central pillars of enclosure D are oriented. The specific imagery carved on the pillars, including vultures, scorpions, foxes, cranes, and a series of abstract symbols whose precise meaning remains debated, has been interpreted by some researchers as incorporating astronomical symbolism, with the vulture in particular proposed as a representation of the constellation Sagittarius or as a symbol associated with the Milky Way. Whether or not the specific astronomical interpretations proposed for Göbekli Tepe are ultimately confirmed by further research, the site's existence demonstrates that the impulse to create large, labor-intensive structures whose design expressed a specific relationship with the sky was present in human communities more than 12,000 years ago, in a period whose astronomical practices leave almost no other recoverable trace. Fact 26. The astronomical instruments of the Islamic world, precision before the telescope. The development of precision astronomical instruments in the Islamic world between the 8th and 15th centuries CE, the refinement and elaboration of the astrolabe, construction of enormous meridian quadrants and sextants for measuring the positions of the sun and stars with maximum accuracy, and the invention of new instruments including the equatorium and the torquetum, whose specific functions addressed particular computational and observational challenges, represents one of the most productive periods of instrumental development in the entire pre-telescopic history of astronomy, driven by the specific combination of practical demand, mathematical sophistication, and material resources that characterized Islamic civilization at its scientific peak. The astrolabe, the most versatile and most widely used astronomical instrument of the medieval world, a flat disc of brass or bronze whose specific design, based on the stereographic projection of the celestial sphere onto a plane, allowed it to be used for a remarkable range of astronomical and practical calculations, including the determination of the time of day or night from stellar observations, the calculation of the times of sunrise and sunset, the determination of the direction of Mecca for the performance of the required daily prayers, the casting of horoscopes, and the solution of spherical trigonometry problems, was known in the Greek world from at least the 2nd century BCE, but was significantly elaborated and refined by Islamic craftsmen and mathematicians whose contributions transformed it from a demonstration instrument into a precision tool of extraordinary utility. The most spectacular Islamic contribution to astronomical instrumentation was the construction of enormous fixed observing instruments, the great stone or masonry quadrants and sextants built at the observatories of Maragha, Samarkand and Istanbul, whose enormous radius, in the case of the Samarkand sextant built by Ulugh Beg in the 15th century, reaching approximately 40 meters, allowed the positions of stars and planets to be measured to an accuracy of arc minutes rather than the degrees achievable with handheld instruments, and whose specific measurements provided the empirical foundation for Ulugh Beg's star catalogue, the most accurate stellar position catalogue produced by any astronomer before the invention of the telescope. Fact 27. Dendera Zodiac, Egypt meets Greece in stone. The Dendera Zodiac, the large circular bas-relief carving discovered on the ceiling of a small chapel in the Temple of Hathor at Dendera in Upper Egypt, dated to approximately 50 BCE and therefore produced in the Ptolemaic period, when Greek cultural influence had transformed many aspects of Egyptian intellectual life, now preserved in the Louvre in Paris after its removal from the temple's ceiling by French engineers in 1820 CE, is the oldest known complete representation of the 12 signs of the zodiac as a unified circular system, and one of the most discussed artifacts in the history of ancient astronomy, both for the specific astronomical content it encodes and for the remarkable debate about its date and meaning that consumed the attention of European scholars from the time of its discovery through much of the 19th century. The carving depicts the 12 zodiacal constellations arranged in a circle around the central north celestial pole, accompanied by the 36 Egyptian decans in an outer ring, the 5 planets visible to the naked eye in their positions relative to the zodiacal constellations, and a rich iconographic surround of Egyptian, astronomical and mythological figures whose specific arrangement expresses the specific synthesis of Egyptian and Greek astronomical traditions that characterized intellectual life in Ptolemaic Egypt. The specific astronomical content of the Dendra zodiac, the positions of the sun, moon, and planets depicted in the carving relative to the zodiacal constellations, was used by scholars in the early 19th century, including the mathematician Jean-Baptiste Fourier, to attempt to determine the date at which the sky configuration it depicted had actually occurred. Applying the astronomical dating method that Hipparchus and the Babylonians had made possible, but that would not be applied to Egyptian monuments on a systematic basis until the development of Egyptology as a discipline. The specific positions of the celestial bodies depicted in the carving correspond most closely to the sky configuration of approximately 50 BCE, consistent with the archaeological dating of the chapel, in which it was found, and confirming that the carving depicts a specific observed sky rather than a schematic representation. Fact 28. The observatory of Tycho Brahe's precursors, Ulugh Beg and Samarkand. Ulugh Beg, the Timurid prince and astronomer, who ruled the city of Samarkand, in what is now Uzbekistan as governor and later as sultan, between approximately 1409 and 1449 CE, who founded the greatest astronomical observatory of the pre-telescopic world on a hill above the city in approximately 1420, and who devoted the central decades of his reign not to military conquest or political expansion, but to the specific project of producing the most accurate measurements of the positions and motions of the celestial bodies achievable with the instruments and methods of his time, is the last great figure in the tradition of Islamic observational astronomy, the culminating representative of a 6th century tradition of precision sky measurement whose specific achievements, while superseded by the telescopic revolution that followed a century and a half after his death, established the observational standards that Tycho Brahe in Denmark and Jai Singh II in India would inherit and build upon in the following centuries. The Samarkand Observatory was built around a single enormous instrument, a meridian sextant of approximately 40 meters radius, constructed in a trench cut into the hillside and aligned precisely north-south, whose specific purpose was to measure the altitude of the sun and stars as they crossed the meridian with the maximum possible accuracy. The instrument's enormous scale, the arc of the sextant spanning 3 floors of the observatory building that was constructed around it, provided a precision of angular measurement approaching 1 arcminute, far exceeding the capabilities of any portable instrument and allowing the systematic measurement of stellar positions to an accuracy previously unachieved. Ulugh Beg used this instrument, over approximately 30 years of observation, to produce the Zij-i-Sultani, a comprehensive star catalogue giving the positions of 1,018 stars, measured afresh from observation, rather than simply copied and corrected from Ptolemy's catalogue, as most medieval astronomical tables had been. The specific accuracy of Ulugh Beg's stellar positions, typical errors of approximately 1 to 2 arcminutes compared to the modern values, was not surpassed until Tycho Brahe's work in the late 16th century. Fact 29. The Nebra Sky Disk, Europe's oldest astronomical artifact. The Nebra Sky Disk, the bronze disk approximately 30 centimeters in diameter, decorated with gold symbols representing the sun or full moon, a crescent moon, and a cluster of stars whose specific pattern corresponds to the Pleiades star cluster, recovered by illegal metal detectorists from a hilltop near the town of Nebra in Saxony-Anhalt, Germany in 1999, and dated by the associated artifacts and by metallurgical analysis to approximately 1600 BCE, placing its manufacture in the Central European Bronze Age, is the oldest known portable representation of specific astronomical phenomena anywhere in the world, and an artifact whose specific content reveals a level of astronomical sophistication in Bronze Age Central Europe whose existence was not previously suspected, and whose specific implications for the understanding of Bronze Age intellectual life have been the subject of intense archaeological and archaeoastronomical debate since the disk's acquisition by the state of Saxony-Anhalt in 2002, after a complex legal process following its illegal excavation. Specific astronomical content of the disk has been interpreted by the archaeoastronomer Wolfhard Schlosser and other researchers as representing a sophisticated agricultural calendar device whose specific function was to harmonize the lunar and solar calendars, a problem that every agricultural civilization must solve, since the lunar month of approximately 29.5 days does not divide evenly into the solar year of approximately 365.25 days, creating a progressive divergence between a purely lunar calendar and the solar seasons on which agricultural scheduling depends. The specific solution implemented in the Nebra disk, according to this interpretation, involves the Pleiades star cluster, whose heliacal rising in spring and heliacal setting in autumn served as agricultural markers in many ancient cultures, and the crescent moon, whose position relative to the Pleiades at specific times of year signals whether an intercalary month needs to be added to the lunar calendar to keep it in alignment with the solar seasons. If this interpretation is correct, the Nebra sky disk represents not merely a representation of the sky, but a functional astronomical instrument encoding a specific calendrical rule of considerable sophistication, produced by a Bronze Age community in Central Europe whose astronomical knowledge was far more advanced than their lack of a written tradition might otherwise suggest. Fact 30. Ancient astronomy at 30. Reading the universe before writing. 30 facts into the story of ancient astronomy, and the full geographic and cultural sweep of the subject has come into view. We have moved from the baboon bone of Lebombo to the bronze gears of the Antikythera mechanism, from the painted ceiling of Senenmut's tomb to the bark paper pages of the Dresden Codex, from the megalithic alignments of Newgrange to the 40-meter sextant of Ulugh Beg's Samarkand observatory. We have understood that the sky was the first shared human interest, the one subject whose study was independently undertaken by every civilization that ever existed in every corner of the world, long before those civilizations had any contact with each other, because the sky was always there, available to every human eye, posing the same questions in every latitude, and demanding the same combination of patient observation and systematic thought from every culture that took it seriously. And we have understood that the specific answers those cultures found, the specific mathematical techniques of Babylon, the specific geometric models of Greece, the specific computational cycles of the Maya, the specific navigational star compass of Polynesia, were not merely anticipations of the modern astronomical tradition, but achievements in their own right, whose specific intellectual character deserves to be understood and appreciated on its own terms, rather than only as a prologue to the science that came after. 70 facts remain. They will carry us through the full depth of the ancient astronomical world, through the specific instruments and the specific observations, the specific myths and the specific mathematics, the specific people whose names we know and the far larger number whose names have been lost, but whose careful attention to the sky built the foundation on which every subsequent understanding of the cosmos has rested. This is explored during sleeping. Fact 31. The constellations, stories written in stars. The constellations, the specific patterns of stars that human cultures across the world have identified, named, and incorporated into mythological narratives, navigational systems, calendar frameworks, and cosmological traditions since the earliest periods of human prehistory, are not objective features of the sky but cultural constructions. The specific groupings of stars that human eyes and human minds have imposed on the random distribution of points of light across the celestial sphere, connecting the dots in patterns whose particular shapes and stories reflect the specific preoccupations, the specific landscape, and the specific cultural imagination of the civilization that created them. The 48 constellations of the classical Western tradition, the set first systematically catalogued by Ptolemy in the Almagest, and whose specific membership, with 40 additions made in the early modern period to cover the southern sky not visible from the Mediterranean, constitutes the modern set of 88 internationally recognized constellations, are the direct descendants of the Babylonian constellation tradition. Transmitted through Greek astronomy in the specific form that Ptolemy's catalogue fixed for all subsequent Western astronomical practice. The mythological narratives associated with the classical constellations, Orion the Hunter, Scorpius the Scorpion, Perseus and Andromeda, the bears of Ursa Major and Minor, are Greek narratives attached to Babylonian star patterns, a specific cultural synthesis whose particular character reflects the double inheritance of the Western astronomical tradition. The specific star patterns recognized as constellations by other astronomical traditions. The Chinese system of approximately 280 small asterisms, very different in membership from the Western constellations. The Indian nakshatra system of 27 or 28 lunar mansions, marking the moon's nightly positions. The Aboriginal Australian tradition that identifies constellations not only in the stars, but in the dark clouds of the Milky Way. demonstrate that the specific way any culture divides the sky into meaningful patterns is a cultural choice, not a natural fact, and that the particular sky maps different civilizations have created are as revealing of their specific values and their specific relationship with the natural world as any other cultural artifact they have produced. Fact 32. Eclipses in the ancient world, omens that terrified civilizations. The specific experience of a solar eclipse in the ancient world, the sudden, unexpected darkening of the midday sky as the moon's shadow swept across the earth, the temperature dropping, the birds falling silent, the stars appearing in what had been a bright blue afternoon sky, and the sun itself reduced to a black disk surrounded by the ghostly corona that ordinary daylight always hides, was among the most psychologically overwhelming natural experiences available to a pre-scientific observer. A phenomenon of such dramatic unexpectedness and such apparent violation of the natural order that virtually every ancient civilization interpreted it as a cosmic omen of the gravest significance, a sign that the sun, the source of light and warmth and agricultural productivity, identified in most ancient religious traditions with a deity of supreme importance, was under attack, was dying, or was expressing its displeasure with the human world below. The specific cultural responses to solar eclipses in the ancient world were diverse but consistently intense. In ancient China, the occurrence of a solar eclipse was interpreted as an attack on the sun by a celestial dragon, and the response, the beating of drums, the shooting of arrows into the sky, the production of as much noise as possible by the assembled court and populace, was a ritual attempt to frighten the dragon away and restore the sun to its full brightness. In ancient Mesopotamia, the eclipse was interpreted as a specific threat to the life of the king, and the specific Babylonian response involved the substitution of a temporary king, a condemned criminal placed on the throne for the duration of the period of danger, who would absorb any evil omen directed at the legitimate monarch and then be killed to complete the ritual, while the real king went into hiding under false identity. The specific Babylonian achievement of eclipse prediction, the identification of the Saros cycle that allowed future eclipses to be anticipated from the pattern of past ones, transformed the experience of the eclipse from an unexpected terror into a predictable, if still awe-inspiring, astronomical event. And the specific knowledge that an eclipse was coming in advance gave Babylonian astronomers both the practical ability to warn their rulers and the intellectual satisfaction of having mastered one of the sky's most dramatic phenomena. Fact 33. The ancient Egyptian decans, a clock made of stars. The decans, the specific system of 36 star groups used by ancient Egyptian astronomers to divide the night into hours, to mark the passage of the year, and to organize the complex astronomical ceiling paintings and coffin lid decorations that represent some of the most sophisticated expressions of Egyptian astronomical knowledge in the surviving record, are one of the most distinctive and most purely Egyptian contributions to the history of ancient astronomy. A system developed independently in the Nile Valley, without any known parallel in other ancient astronomical traditions, and whose specific character, combining the practical timekeeping function of a star clock with the religious and funerary significance of the stars as souls of the dead, reflects the specific integration of astronomical and theological knowledge that characterized Egyptian intellectual life. The specific astronomical basis of the Deccan system was the observation that the sky could be divided into 36 groups of stars whose successive heliacal risings, the first appearance of each group on the eastern horizon just before sunrise after a period of invisibility, were spaced approximately 10 days apart, dividing the 360-day schematic Egyptian year into 36 decades of 10 days each. Each decan rose heliacally for approximately 10 days before the next decan took its turn, creating a star calendar whose specific marker was not the position of the sun, but the identity of the decan rising on the eastern horizon at dawn. During the night, the sequence of decans crossing the eastern horizon provided a star clock. Since approximately 12 decans rose between sunset and sunrise at the latitude of Egypt, the rising of each successive decan marked the passage of approximately 1 hour of night, allowing an observer who knew the decan sequence to determine the approximate hour of the night from the observation of which decan was rising. The specific funerary significance of the decans was their identification, in the Egyptian religious tradition, with specific deities whose specific powers were relevant to the deceased's journey through the underworld, making the astronomical ceiling of a tomb simultaneously a star map, a clock, a calendar, and a theological statement whose specific dimensions have occupied Egyptologists since the detailed study of these ceilings began in the 19th century. Fact 34. The Baghdad Observatory and the House of Wisdom, where ancient and Islamic science met. The House of Wisdom, the great intellectual institution established in Baghdad in the late 8th century CE under the patronage of the Abbasid Caliph Harun al-Rashid, and expanded to its greatest influence under his son Al-Mamun, who ruled from 813 to 833 CE, and whose specific personal interest in astronomy and mathematics drove the most ambitious program of scientific patronage in the early Islamic world. It was not a single building or a single institution in the modern sense, but a complex of libraries, translation bureaus, and scholarly workshops whose combined activity over the 9th and 10th centuries CE produced the most concentrated episode of scientific transmission and innovation in the history of the ancient and medieval world, bringing together in a single city the intellectual traditions of Greece, Persia, India, and the indigenous Islamic mathematical and astronomical tradition, and fusing them into a synthesis whose specific productivity would transform the history of science. The specific astronomical activity supported by Al-Mamun's patronage included a comprehensive program of new astronomical observations designed to verify, and, where necessary, correct the values given in Ptolemy's Almagest and the Indian astronomical texts that had been translated into Arabic in the preceding generation. Al-Mamun commissioned the construction of 2 new observatories, one in Baghdad and one near Damascus, equipped with instruments of the highest available quality, at which teams of astronomers conducted systematic observations of the Sun, Moon, and planets over sustained periods designed to produce the long baseline of observational data needed to measure slowly varying astronomical quantities with high precision. The specific results of these observations, the corrected values of the precession of the equinoxes, the obliquity of the ecliptic, the solar parameters, were incorporated into new astronomical tables called Zijs that became the standard reference works of Islamic astronomy for generations, and whose specific quality represented a significant advance over the values in Ptolemy's Almagest that they partially superseded. Fact 35. Stonehenge's true purpose, the debate that never ends. The question of Stonehenge's purpose, the specific function or functions that the monument served for the communities that built it, and used it across the 2,000-year period of its construction and active use, from the first earthwork enclosure of approximately 3000 BCE through the erection of the Sarsen stones in approximately 2500 BCE to the final modifications of the Late Bronze Age, is one of the most extensively debated questions in the archaeology of prehistoric Britain, generating more scholarly publications, more popular books, and more competing hypotheses than any other single archaeological question in the British Isles, and remaining, despite more than 3 centuries of investigation, genuinely and perhaps irreducibly uncertain in its specific answer. Though the range of plausible interpretations has been significantly narrowed by the accumulating evidence of modern archaeological research. The astronomical hypothesis that Stonehenge was primarily or significantly an astronomical monument, used to mark the solstices and equinoxes and possibly to predict eclipses, has been the most influential interpretive framework in the popular understanding of the monument since the astronomer Gerald Hawkins proposed, in his 1965 book Stonehenge, decoded that many of the specific alignments of stones and holes at the monument could be used to predict the rising and setting positions of the Sun and Moon, and even the occurrence of eclipses. The specific eclipse prediction hypothesis, based on Hawkins's proposal that the 56 Aubrey holes, the circular series of chalk-filled pits that constitute the oldest feature of the monument, could have been used as a counting device for tracking the 18-year Saros cycle, has been extensively discussed and generally regarded by professional archaeologists as unproven, since no direct evidence of its use for eclipse prediction has been recovered from the archaeological record. What is not disputed is the specific solar alignment of the monument's main axis, the orientation toward the midsummer sunrise and midwinter sunset that is too precise to be accidental, and that demonstrates, whatever the monument's full range of purposes, that the observation and marking of the solar cycle was a central and deliberate component of its design. Fact 36. The Antikythera mechanism's secrets, what the X-rays revealed. The progressive revelation of the full content of the Antikythera mechanism, the ancient Greek mechanical computer, whose broad outlines were established by early investigators, but whose specific details, including the complete gear train, the full text of the inscriptions, and the specific astronomical functions of all the dials and pointers, have been recovered only gradually over more than a century of increasingly sophisticated analysis, is one of the most compelling stories in the history of the archaeology of ancient science, a detective narrative in which successive generations of researchers have applied the best available imaging and analytical technology to the corroded fragments of an object whose extraordinary complexity reveals itself more fully with each new investigation. The initial investigation of the mechanism by the Greek archaeologist Valerios Stais in 1902 established the presence of bronze gears, and inscribed text in the corroded fragments recovered from the Antikythera shipwreck. But the true complexity of the mechanism was not appreciated until the British physicist Derek de Solla Price undertook the first systematic analysis of the fragments in the 1950s and 1970s. Proposing a reconstruction that identified approximately 30 gears and several astronomical functions, but left many aspects of the mechanism unresolved. The application of three-dimensional X-ray computed tomography to the fragments by a British-Greek research team in 2005 and 2006 was transformative. The CT scans revealed the complete gear train in 3 dimensions, allowing the precise tooth counts of gears hidden deep within the corroded fragments to be determined for the first time, and revealed thousands of previously unread inscription characters on the interior surfaces of the mechanism's bronze plates, whose partial decipherment has provided the most detailed picture yet of the mechanism's specific astronomical functions. The 2006 analysis confirmed the presence of a planetary display mechanism on the front face of the device, showing the positions of the 5 classical planets, Mercury, Venus, Mars, Jupiter, and Saturn, as well as the Sun and Moon, and a back face containing the Metonic calendar spiral, the Saros eclipse prediction dial, and the games dial showing the 4-year cycle of the Pan-Hellenic athletic festivals, making it a device of even greater astronomical and practical scope than any previous reconstruction had proposed. Fact 37. Aboriginal Australian Astronomy, the oldest living sky tradition. The astronomical knowledge of Aboriginal Australians, the specific body of sky knowledge developed, refined, and transmitted through oral tradition and ceremony by the Indigenous peoples of Australia across a period that may extend to more than 65,000 years of continuous occupation of the Australian continent, making it almost certainly the oldest continuously practiced astronomical tradition in the history of the human species, is a subject that has received increasing scholarly attention in recent decades. As researchers working in collaboration with Aboriginal knowledge holders have begun to document the remarkable sophistication and the specific practical and cosmological dimensions of a tradition whose specific character differs profoundly from the mathematical and observational astronomy of the Old World traditions, but whose specific achievements in the identification of astronomical cycles, the development of ecological calendars based on stellar events, and the creation of a rich cosmological narrative that integrates the sky into every dimension of the Aboriginal relationship with the land, are no less impressive for their different cultural form. The most distinctive feature of Aboriginal Australian astronomy is the tradition of identifying constellations, not only in the patterns of bright stars, but in the dark nebulae, the dust clouds and dark regions of the Milky Way, whose specific shapes were identified and named as the dark constellation system, a practice unique to Aboriginal Australian astronomical tradition among all the sky traditions of the world. The specific dark constellations of the Australian tradition include the Emu in the sky, a constellation formed by the dark nebulae of the Milky Way whose specific shape, a long-necked bird with a body and legs, is visible in the southern autumn sky, and whose specific appearance and orientation serve as an ecological calendar marker. The rising of the emu's head in the eastern sky at dusk in April or May, signaling the time when emus are sitting on their nests and their eggs are accessible for collection. The specific ecological calendar function of the emu constellation, and of the numerous other stellar and dark constellation markers used by different Aboriginal communities to time the appearance of specific food resources, the migration of animals, the flowering of plants, and the onset of seasonal weather patterns, demonstrates that Aboriginal astronomical knowledge was not merely cosmological or ceremonial but deeply practical. Embedded in the specific ecological knowledge that sustained human life in the diverse and often harsh environments of the Australian continent. Fact 38. The Maragha Revolution, when Islamic astronomers challenged Ptolemy. The Maragha Revolution, the specific critical movement in Islamic astronomy, centered on the observatory, founded at Maragha in northwestern Iran in 1259 CE by the Mongol ruler Hulagu Khan under the direction of the polymath Nasir al-Din al-Tusi, and continued by a succession of brilliant astronomers including Al-Urdi, Ibn al-Shatir, and Al-Qushji over the following 2 centuries. Represents the most sustained and most technically sophisticated challenge to the Ptolemaic astronomical tradition in the history of pre-Copernican astronomy, and the specific intellectual movement whose particular achievements, the identification of specific mathematical contradictions within the Ptolemaic model, and the development of alternative mathematical devices to resolve them, have been recognized by historians of science as the direct intellectual predecessor of the Copernican revolution, providing specific mathematical tools that Copernicus himself appears to have used in constructing his heliocentric model. The specific problem that motivated the Maragha astronomers was the equant, the specific geometrical device that Ptolemy had introduced into his planetary models to reproduce the observed non-uniform motion of the planets, which required that each planet move at a uniform angular velocity, not around the center of its own orbit, but around a separate point called the equant, offset from the center in the direction opposite to the Earth. The equant was mathematically effective. It allowed the Ptolemaic model to reproduce the observed planetary motions with good accuracy, but it violated the specific physical principle that had governed Greek astronomical theorizing from its earliest period, the principle that all celestial motions must be composed of uniform circular motions. Al-Tusi addressed this problem by developing a specific mathematical device, now known as the Tusi couple, consisting of two circles, one rotating inside the other at twice the speed, whose combined motion produces a straight-line oscillation that can be used to replace the equant while maintaining strict adherence to uniform circular motion. The Tusi couple appears, in essentially identical form, in Copernicus's heliocentric model published in 1543, raising the specific historical question, still debated by historians of science, of whether Copernicus encountered and used the mathematical work of the Maragha astronomers through some channel of transmission whose specific nature has not yet been established. Fact 39. The ancient Chinese observation of the 1054 supernova, a star that changed the sky. The appearance in July 1054 CE of a new star, a star that had not been present in the sky the previous night, and that was, for the first few weeks of its visibility, bright enough to be seen in broad daylight and visible to the naked eye for approximately 2 years before gradually fading below the threshold of unaided vision, was recorded by Chinese and Japanese astronomers with the specific observational detail and the specific institutional diligence that the continuous skywatching practice of the East Asian astronomical traditions made routine. Producing in the Chinese imperial astronomical records and the Japanese court diaries of the period a set of observational reports whose specific content has allowed modern astronomers to identify the 1054 event as the supernova explosion that created the Crab Nebula. The expanding cloud of gas and the rapidly rotating neutron star at its center that modern radio and X-ray telescopes have revealed as the specific remnant of one of the most energetic events to occur in the vicinity of the solar system in the past 10,000 years. The Chinese records preserved in the official histories of the Song dynasty describe the appearance of a guest star, the standard Chinese term for any new stellar object, whether comet, a nova or a supernova in the constellation of Tiangyuan, corresponding to the star Zeta Tauri in the modern constellation of Taurus, on a specific date in the third month of the first year of the Zhe era, corresponding to July 4, 1054 CE in the modern calendar. The record notes that the guest star was visible in daylight for 23 days and remained visible at night for approximately 2 years before disappearing, and that its color was reddish-white, a specific chromatic description consistent with the expected visual appearance of a supernova at its maximum brightness. The specific absence of any comparable record in the European chronicles of the period, despite the fact that the 1054 supernova would have been clearly visible from Europe and was certainly bright enough to attract the attention of any skywatcher, is a testimony to the specific difference in astronomical culture between a civilization that maintained continuous, institutionalized skywatching as an imperial obligation and a medieval European culture that, in 1054 CE, had no comparable institutional framework for the systematic monitoring and recording of celestial phenomena. Fact 40. Ancient astronomy at 40, halfway through the sky. 40 facts into the story of ancient astronomy, and we have reached the midpoint of a journey that began with the first human being who looked up at the night sky and understood that the lights moving across it were not random but regular, that the same stars rose and set in the same positions night after night, that the moon completed its cycle of phases in the same number of days month after month, and that somewhere in this regularity was information of the most practical and the most profound kind available to a creature whose survival depended on knowing when to plant, when to sail, when to seek shelter, and where to find the places on Earth that the stars could lead to. We have crossed the Pacific in a Polynesian canoe guided by a star compass carried in memory. We have sat with Al-Tusi at Maragha and understood that the specific mathematical device he invented to rescue Ptolemy's system from its internal contradictions was the same device that Copernicus would use, centuries later, to build the heliocentric model that eventually replaced it. We have looked at the night sky through Aboriginal Australian eyes and understood that the dark clouds of the Milky Way can be read as an emu settling on its nest, and that the specific moment when that emu appears in a particular position in the eastern sky at dusk tells a knowledgeable observer that the emus are nesting and their eggs can be found. 60 facts remain. They will carry us through the observatories and the instruments, the specific myths and the specific mathematics, the specific cultures and the specific people whose accumulated attention to the sky built the most ancient and most universal science that the human mind has ever practiced. This is explored during sleeping. Fact 41. The astronomical knowledge of the Inca, reading the sky from the roof of the world. The astronomical tradition of the Inca Empire, the vast Andean civilization that at its greatest extent in the 15th and early 16th centuries, CE governed a territory of approximately 2 million square kilometers along the western coast of South America, from modern Colombia in the north to central Chile in the south, and whose specific astronomical knowledge was embedded in a cosmological, religious, and calendrical framework of extraordinary complexity, whose particular character reflected the specific environment of the high Andes and the specific needs of an agricultural civilization, dependent on the precise timing of planting and harvesting across a range of ecological zones at dramatically different altitudes, represents one of the most sophisticated astronomical traditions in the pre-Columbian Americas, and one whose specific recovery has been complicated by the near-total destruction of the written and material record by the Spanish conquest and the subsequent suppression of indigenous religious practices. The Inca capital of Cusco was organized as a cosmological map, a city whose specific layout incorporated astronomical alignments, whose central sacred space, the Coricancha or Temple of the Sun, served simultaneously as the religious center of the empire, the primary astronomical observation site, and the origin point of the SEC system, a network of 41 imaginary lines radiating from the Coricancha in all directions, along whose specific paths were located approximately 328 sacred sites, called huarcas, whose particular positions encoded an astronomical calendar, dividing the year into the specific intervals needed for the scheduling of agricultural and religious activities. The Inca astronomical tradition incorporated both stellar and dark cloud astronomy, the identification of dark nebulae in the Milky Way as specific animal constellations, whose appearance and movement marked the seasons and guided agricultural practice, sharing with the Aboriginal Australian tradition the specific practice of reading the sky in its dark regions as well as its bright ones. A coincidence that reflects the specific advantage of dark cloud constellation observation from the southern hemisphere, where the galactic center and its associated dark nebulae are more prominently placed in the sky than they appear from the northern latitudes of the Old World astronomical traditions. Fact 42. The first measurement of the speed of light, an astronomical accident. The first measurement of the speed of light, an achievement accomplished not in a laboratory, but through the careful analysis of astronomical observations, not by a physicist but by an astronomer, and not as the result of an experiment designed for the purpose, but as the explanation of an anomaly that no existing theory could account for, was made by the Danish astronomer Ulugh Beg in 1676, working at the Paris Observatory under the direction of Giovanni Cassini. Using observations of the timing of the eclipses of Jupiter's innermost large moon Io as the specific dataset from which the finite speed of light could be inferred, the specific observation that led to Romer's discovery was the systematic discrepancy between the predicted and observed times of Io's eclipses, the moments when Io disappeared behind Jupiter's disk or reappeared from Jupiter's shadow that accumulated in a specific and directional way over the course of a year. When the Earth was moving toward Jupiter in its orbit, the observed eclipses occurred slightly earlier than predicted. When the Earth was moving away from Jupiter, they occurred slightly later. The accumulated discrepancy over the course of 6 months, approximately 22 minutes in Romer's original calculation, was precisely what would be expected if light took a finite time to travel from Jupiter to the Earth, and if the difference in travel time between the Earth's closest and farthest points from Jupiter corresponded to the time required for light to travel the diameter of the Earth's orbit. Romer's calculation of the speed of light from this reasoning, approximately 220,000 kilometers per second, compared to the modern value of approximately 299,792 kilometers per second, an underestimate of approximately 26% attributable to errors in the then known value of the Earth's orbital radius and in the accumulated timing discrepancy, was the first finite measurement of a quantity that many natural philosophers of the time believed was instantaneous, and it demonstrated that the astronomical scale of the solar system, newly understood through Kepler's laws and Newton's gravitational theory, provided a baseline large enough to measure phenomena that were entirely unmeasurable at terrestrial scales. Fact 43. The astronomy of ancient Persia, Zoroastrian skis. The astronomical tradition of ancient Persia, the sky knowledge developed and maintained by the successive civilizations of the Iranian plateau, from the Elamite and early Iranian cultures of the 3rd and 2nd millennia BCE through the Achaemenid and Sassanid Persian empires, and into the early Islamic period, when Persian scholars became the primary transmitters and advancers of the astronomical knowledge they had inherited from both the Babylonian and Greek traditions. Was shaped throughout its history by the specific cosmological framework of the Zoroastrian religion, the ancient Iranian faith whose dualistic theology of light and darkness, good and evil, assigned specific cosmic significance to the celestial lights, the sun, the moon, and the stars, as the specific manifestations of the divine principle of light in the eternal struggle against the principle of darkness. The specific astronomical content of the Zoroastrian cosmological tradition is preserved in the Avesta, the sacred scriptures of the Zoroastrian religion, and in the Bundahishan, a Middle Persian text of the Sassanid period that provides an extensive account of the Zoroastrian understanding of the cosmos, including the specific positions and functions of the stars, the movements of the planets, and the specific relationship between celestial events and the theological drama of the cosmic struggle between Ahura Mazda, the principle of light and creation, and Angra Mainyu, the principle of darkness and destruction. The specific contribution of Persian astronomy to the broader development of ancient astronomical knowledge was primarily the role of Persia as a cultural bridge, the specific geographic and political position of the successive Persian empires at the crossroads of the Babylonian, Greek, and Indian astronomical traditions allowed Persian scholars to serve as the principal transmitters of Babylonian astronomical knowledge westward into the Hellenistic world and eastward into the Indian subcontinent, and later as among the most important contributors to the great translation movement of the early Islamic period that brought the Greek astronomical tradition into Arabic and set the stage for the Islamic golden age of astronomical achievement. Fact 44. The Venus of Lawsel, the moon counter of the Ice Age. The Venus of Lawsel, the bas-relief carving of a female figure approximately 46 centimeters high, cut into the limestone wall of a rock shelter in the Dordogne region of southwestern France during the Gravettian period of the Upper Paleolithic, dated to approximately 25,000 years ago, and depicting a female figure holding in her raised right hand a bison horn bearing 13 notches, whose specific number corresponds to both the number of lunar months in a year and the average number of days in a human menstrual cycle, is one of the most discussed and most interpreted artifacts in the archaeology of prehistoric human cognition, and one that has been at the center of an ongoing debate about the antiquity of the specific connection between the lunar cycle and the female reproductive cycle that several researchers have proposed as a foundational moment in the development of human astronomical awareness. The specific interpretation of the 13 notches on the horn held by the Lawsel figure as a representation of lunar counting, proposed most influentially by the researcher Alexander Marshak in his 1972 book, The Roots of Civilization, and subsequently developed and debated by numerous researchers in the fields of Paleolithic archaeology and cognitive evolution, rests on the specific numerical correspondence between the 13 notches and both the number of full moons in a solar year and the average length of the human menstrual cycle in days, and on the specific visual association of the horn, whose crescent shape in the relief may represent the crescent moon, with the counting marks. Whether or not the specific interpretation of the Lawsel figure as a lunar counter is correct, and it remains debated, as all interpretations of Paleolithic art necessarily do in the absence of written explanation. The figure belongs to a broader pattern of notched bones, ivory plaques, and other marked objects from the Upper Paleolithic, whose specific numerical content has been extensively analyzed as potential evidence of early astronomical counting, and whose collective weight has led many researchers to conclude that systematic attention to the cycles of the moon was a feature of human cognitive life long before the development of any other form of systematic record-keeping. Fact 45. The astronomical orientation of the Great Pyramid, precision in stone. The Great Pyramid of Giza, the tomb of the pharaoh Khufu, constructed approximately 2560 BCE on the Giza Plateau west of the Nile near modern Cairo, the oldest of the 7 wonders of the ancient world, and the only one still standing, whose original height of approximately 146.5 meters made it the tallest structure on Earth for more than 3,800 years, is aligned to the cardinal points of the compass with a precision that has fascinated and perplexed researchers since the first accurate surveys of the monument were undertaken in the 19th century, its 4 sides oriented to true north, south, east, and west with an error of less than 1/15 of a degree. A precision that required both an accurate method for determining true north and the specific engineering skill to implement that determination in the placement of a structure covering approximately 53,000 square meters of ground. The specific method by which the ancient Egyptian surveyors determined true north with such extraordinary precision has been the subject of debate among archaeologists and archaeoastronomers for more than a century, with several competing hypotheses proposed whose specific merits and limitations depend on the precise nature of the observational technique assumed and the specific astronomical conditions prevailing at the time of the pyramid's construction. The most widely accepted current hypothesis, proposed by the archaeoastronomer Kate Spence in a 2000 paper in the journal Nature, suggests that the Egyptian surveyors determined true north by observing the simultaneous transit of two circumpolar stars, Kochab in Ursa Minor and Mizar in Ursa Major, across the meridian, using the specific moment when these two stars aligned vertically as seen from the observation point as the indicator of the true north direction. This method would have been applicable only at a specific historical period, when the slow precession of the Earth's axis brought these two particular stars into the specific configuration required, and Spence's calculation of this period yields a date of approximately 2478 BCE, consistent with the archaeological dating of the pyramid's construction. Whatever method was actually used, the specific accuracy of the Great Pyramid's orientation, achieved without metal instruments, without telescopes, and without any of the technological infrastructure of modern surveying, remains one of the most impressive demonstrations of ancient observational and engineering capability in the entire archaeological record. Fact 46. Ibn al-Haytham, the man who understood how we see the sky. Ibn al-Haytham, the Arab mathematician and natural philosopher born in Basra in approximately 965 CE, and known in the Latin West as Alhazen, who spent the most productive period of his career in Cairo under the Fatimid Caliphate, and who produced in his monumental 7-volume Book of Optics a comprehensive mathematical theory of vision and light whose specific content, including the correct identification of the eye as a passive receiver of light rather than an active emitter, the analysis of refraction and reflection, and the development of the camera obscura as an investigative tool, established him as the founder of the science of optics in the modern sense. Made specific contributions to astronomical observation and theory, whose particular character illustrates the specific way in which advances in the understanding of light and vision directly affected the interpretation of what astronomers actually saw when they looked at the sky. Ibn al-Haytham's most significant astronomical observation was his analysis of the specific optical phenomenon known as astronomical refraction, the bending of light from celestial objects as it passes through the Earth's atmosphere, which causes stars and planets near the horizon to appear higher in the sky than their true positions, and which creates the specific distortion of the apparent shape of the Sun and Moon near the horizon. Where the bottom of the disk appears raised more than the top, by the greater refraction of the lower, raised through the thicker atmospheric layer they traverse. The specific mathematical analysis of atmospheric refraction that Ibn al-Haytham undertook, the first systematic treatment of this phenomenon in the history of astronomy, was motivated by the specific practical problem that refraction introduced errors into astronomical measurements of the positions of celestial bodies near the horizon, and its correction required the specific quantitative understanding of the effect that only a mathematical treatment could provide. Ibn al-Haytham's analysis established that the atmosphere has a finite height. He estimated approximately 52,000 paces, corresponding to roughly 80 kilometers, and derived the first mathematical model of the refraction effect whose specific predictions, while not highly accurate by modern standards, were a significant improvement over any previous treatment, and established the principle that atmospheric refraction must be accounted for in precision astronomical observations. Fact 47. The Nazca Lines, a desert canvas for the sky. The Nazca Lines, the vast network of geoglyphs etched into the desert surface of the Nazca Plateau in southern Peru between approximately 500 BCE and 500 CE by the Nazca people, consisting of hundreds of geometric figures including straight lines extending for several kilometers, large geometric shapes including triangles, trapezoids, and spirals, and approximately 70 figurative images including animals, plants, and human figures whose specific scale, many visible only in their full extent from the air, has made them among the most discussed and most variously interpreted of all ancient monuments, have been proposed since the astronomer Paul Kosok first suggested an astronomical interpretation in 1941. As a giant astronomical calendar or observatory, whose specific lines were oriented toward the rising and setting points of specific celestial bodies at specific times of year, providing the Nazca people with a sky map of enormous scale whose particular function was to organize the agricultural and religious calendar of a desert civilization whose survival depended on the precise scheduling of planting in relation to the seasonal availability of water. The astronomer Gerald Hawkins, who had also proposed astronomical interpretations of Stonehenge, conducted a comprehensive computer analysis of the orientations of the Nazca lines in the 1960s and found that the proportion of lines oriented towards significant astronomical events, solstice sunrises, major star risings and settings, was no greater than would be expected from random chance. A conclusion that significantly undermined the strongest versions of the astronomical hypothesis. The German archaeologist and mathematician Maria Reich, who dedicated more than 40 years of her life to studying, mapping, and protecting the Nazca lines, maintained a more qualified version of the astronomical hypothesis, proposing that specific groups of lines were oriented toward astronomically significant directions, without claiming that the entire system constituted a single coherent astronomical instrument. The current archaeological consensus acknowledges that some Nazca lines may incorporate astronomical orientations while rejecting the comprehensive astronomical calendar hypothesis, proposing instead that the lines served primarily ritual and ceremonial functions related to water and fertility that incorporated but were not exclusively defined by astronomical references. Fact 48. The Star of Bethlehem, Astronomy Meets History. The Star of Bethlehem, the celestial phenomenon described in the Gospel of Matthew as having appeared at the time of the birth of Jesus of Nazareth, guided the Magi from the east to Jerusalem and then to Bethlehem, and stood over the place where the child lay, has been the subject of astronomical investigation since at least the 17th century. When Johannes Kepler proposed that the specific triple conjunction of Jupiter and Saturn in the constellation of Pisces in 7 BCE, an event whose rarity and whose occurrence in a zodiacal sign associated in Jewish astrological tradition with the destiny of Israel, might have been the astronomical phenomenon that prompted the Magi to undertake their journey westward toward Judea. The specific astronomical investigation of the Star of Bethlehem is complicated by several fundamental uncertainties, whose resolution depends on the interaction of historical, theological, and astronomical questions that cannot be cleanly separated. The specific date of the birth of Jesus is uncertain, with scholarly estimates ranging from approximately 7 BCE to 1 BCE. The specific identity of the Magi and the astrological tradition within which they would have interpreted celestial phenomena is debated. And the specific wording of the Greek text of Matthew's account, whose description of the star's behavior, including the claim that it moved and came to rest over a specific location, is difficult to reconcile with the natural behavior of any known astronomical phenomenon, has been interpreted both as a literal description of a specific celestial event and as a literary motif drawing on the convention of the star of royal nativity found in ancient Near Eastern and Greco-Roman literature. Among the specific astronomical candidates proposed by researchers over the centuries are Kepler's Jupiter-Saturn triple conjunction of 7 BCE, a Jupiter-Venus conjunction of 2 BCE whose specific brilliance would have made it one of the most dramatic planetary conjunctions in living memory, the appearance of Halley's Comet in 12 BCE, and a nova or supernova recorded in Chinese astronomical records in approximately 5 BCE. Each candidate fits some of the historical and textual evidence while failing to account for other aspects of the account, and the specific question of what astronomical event, if any, underlies the Matthew narrative remains genuinely open. Fact 49. The astronomical legacy of Alexander's conquests when Greek and Babylonian science merged. The specific intellectual consequence of Alexander the Great's conquests in the 4th century BCE, the military campaigns that between 334 and 323 BCE brought Greece, Persia, Egypt, and the territories extending to the borders of India under a single political authority for the first time in history, was, among its many other dimensions, the creation of the specific cultural and intellectual environment in which the two most sophisticated astronomical traditions of the ancient world, the Greek geometrical tradition and the Babylonian numerical tradition, came into direct contact for the first time and began the process of mutual influence and synthesis whose specific products, the hybrid Greco-Babylonian astronomy of the Hellenistic period, laid the foundations for the entire subsequent development of Western and Islamic astronomical science. The specific form of this intellectual exchange was the availability, for the first time, of Babylonian astronomical records to Greek scholars working in the cities of the newly created Hellenistic world. Greek mathematicians and philosophers had developed sophisticated geometrical models for understanding the motions of the heavens, but their models were largely divorced from the specific quantitative observational data that would allow their parameters to be accurately determined. The Babylonians possessed exactly what the Greeks lacked: 5 centuries of continuous, precise observations of the positions and motions of the sun, moon, and planets, organized into numerical tables whose specific content provided the empirical foundation on which any accurate predictive model must rest. The Greek astronomer Hipparchus, who was discussed in an earlier fact as the greatest observational astronomer of antiquity, was the specific individual who most fully exploited this synthesis, using Babylonian observational records in combination with his own observations to determine with unprecedented precision the parameters of the Greek geometrical models, producing in the process the most accurate ancient model of the lunar motion and the first comprehensive star catalogue in the Western tradition. The specific historical significance of Hipparchus's synthesis is that it created, for the first time, the specific combination of geometrical modeling and empirical quantitative data that constitutes the essential method of modern mathematical astronomy. Fact 50: Ancient Astronomy at 50, the middle of the sky. 50 facts into the story of ancient astronomy and the full breadth of what ancient human beings knew about the sky and what they did with that knowledge has become fully visible. We have understood that the astronomical knowledge of the ancient world was not a preliminary sketch for the real science that came later, but a series of genuine achievements, made under conditions of extraordinary difficulty, without telescopes, without computers, without any of the instruments of precision that modern astronomy takes for granted, whose specific results were sometimes more accurate than the centuries of effort they cost might seem to justify, and whose specific methods were, at their best, as rigorous and as creative as the best science of any subsequent period. We have watched Polynesian navigators cross the Pacific guided by a star compass that existed only in memory. We have read the sky in the dark nebulae of the Milky Way with Aboriginal Australian eyes and understood that an emu settling on its nest in the Milky Way tells a community that the real emus are nesting below and their eggs can be found. We have held the Dresden Codex and understood that the Maya tracked Venus across the sky with an accuracy of 1 day in 500 years, embedded in a religious and astrological tradition whose specific power was inseparable from the precision of the astronomical knowledge that underpinned it. 50 facts remain. They will carry us through the final half of the ancient astronomical world, through the observatories and the myths, the instruments and the calculations, the specific people whose names the record has preserved, and the vast majority whose names it has not, and through the specific question that every fact in this story has been circling toward. What does it mean that every human civilization that has ever existed looked up at the same sky and found in it, independently and inevitably, the same fundamental order? This is explored during sleeping. Fact 51: The ancient Greek cosmos, spheres within spheres. The specific model of the cosmos developed by Greek natural philosophers and astronomers between the 5th and 2nd centuries BCE. The picture of the universe as a series of concentric crystalline spheres carrying the celestial bodies in their motions around a central, stationary, spherical Earth, the whole enclosed by the outermost sphere of the fixed stars, whose daily rotation produced the apparent daily turning of the sky, was not, as it is sometimes presented in popular accounts of the history of science, a naive or arbitrary construction imposed on the astronomical data for theological or aesthetic reasons, but the specific product of careful reasoning about the observed phenomena of the sky, combined with the specific physical principles that Greek natural philosophy had developed, and whose particular elegance and explanatory power made it the dominant framework for astronomical theorizing for nearly 2,000 years. The specific philosophical foundations of the Greek geocentric cosmos were developed above all by Aristotle, whose comprehensive physical theory assigned to the celestial realm everything above the sphere of the moon, a fundamentally different character from the terrestrial realm below, composed not of the 4 terrestrial elements of earth, water, air, and fire, but of a 5th element, the ether, whose specific properties, weightlessness, incorruptibility, and the capacity for only one kind of natural motion, uniform circular motion, explained why the celestial bodies moved in circles at constant speeds, rather than falling downward as terrestrial objects did. This specific physical theory provided the framework within which Greek mathematical astronomers developed their geometrical models of the planetary motions. The requirement that all celestial motion be composed of uniform circular motions was not an arbitrary aesthetic preference, but a specific deduction from the Aristotelian physical theory of the ether, and the specific challenge of constructing geometric models that reproduced the observed non-uniform planetary motions using only combinations of uniform circular motion, was the defining problem of Greek mathematical astronomy from Plato's time to Ptolemy's and beyond. Fact 52. The lunar mansions, how India and Arabia divided the moon's path. The lunar mansion systems of ancient India and the Islamic world, the specific division of the zodiacal band into 27 or 28 sections of approximately equal width, each corresponding roughly to the distance the moon travels against the background of the fixed stars in a single day, and each associated with a specific star or group of stars whose position marked the moon's location in the sky during its one-day occupancy of that section of the sky, represent one of the most widespread and most practically useful astronomical frameworks developed independently in multiple ancient cultures, appearing in roughly similar form in the Indian nakshatra tradition, the Arabic manzil system, and the Chinese Xiu system. A convergent development whose specific parallel appearance in three distinct astronomical traditions reflects the specific utility of dividing the sky into a number of sections corresponding to the moon's daily motion for the practical purposes of lunar calendar computation and agricultural timing. The Indian nakshatra system, the oldest and most fully developed of the three parallel traditions, divides the zodiacal band into 27 nakshatras of approximately 13 1/3 degrees each one identified by a specific star or asterism whose position marks the nakshatra's location, and each one associated with a specific deity, a specific set of astrological qualities, and specific ritual prescriptions for activities undertaken when the moon is in that nakshatra. The nakshatra system is mentioned in the Rigveda, the oldest surviving text of the Indian literary tradition, dated to approximately 1500 to 1200 BCE, and its specific astronomical content, the identification of the specific stars marking each nakshatra and the specific description of the moon's path through the system, has been used by astronomers and historians to attempt to date the specific period when the nakshatra system was first formalized. Using the precession of the equinoxes to determine which star occupied which position relative to the equinoctial point at different historical periods. The specific conclusions of this dating analysis suggest that the nakshatra system was formalized in approximately the 2nd millennium BCE, consistent with the Rigvedic dating, making it one of the oldest surviving astronomical coordinate systems in any tradition. Fact 53. The Tower of Babel as observatory, ziggurats and the stars. The great step temple towers of ancient Mesopotamia, the ziggurats, those massive multi-terrace structures of mud brick that dominated the skylines of the major Sumerian, Akkadian, Babylonian and Assyrian cities from the 3rd millennium BCE onward, and whose most famous representative in the Western cultural imagination is the Tower of Babel described in the Book of Genesis, served. In addition to their primary function as the elevated platforms on which the shrines of the city's patron deities were constructed, as the specific observational platforms from which the priest astronomers of the Mesopotamian temple establishments conducted the nightly sky observations, whose accumulated records constituted the empirical foundation of the Babylonian astronomical tradition. The specific advantage of the ziggurat as an astronomical observation platform was its elevation above the flat Mesopotamian landscape, in a region where the natural terrain provided no elevated vantage points and the horizon was uniformly flat in all directions. The artificial height of the ziggurat's summit provided its observers with a cleaner lower horizon and a slightly extended field of view that, while modest in absolute terms, was the best available in the specific environment of the Mesopotamian alluvial plain. The specific organization of astronomical observation from the ziggurat platform was an institutional activity conducted by the specialist priest astronomers called Tupsar Enuma Anu Enlil, the scribes of the Great Omen series, whose accumulated observations over 5 centuries constituted the astronomical diaries, rather than the individual activity of an amateur skywatcher, and this institutional character. The embedding of astronomical observation in the specific organizational structure of the Mesopotamian temple establishment was what made possible the sustained, consistent, long-term observational record, whose specific value for the identification of astronomical cycles was recognized by the Babylonian astronomers themselves. The specific height of the Great Ziggurat of Babylon, estimated at approximately 90 meters in its final form under Nebuchadnezzar II in the 6th century BCE, would have provided its observers with a commanding view of the flat Mesopotamian horizon in all directions, making it the most effective naked-eye astronomical observation platform in the ancient Near East. Fact 54. Claudius Ptolemy, the man who named the stars. Claudius Ptolemy of Alexandria, the Greek-speaking Egyptian astronomer, mathematician, geographer, and natural philosopher who worked in Alexandria in the 2nd century CE and whose specific intellectual output, spanning not only the Almagest but also the Tetrabiblos, the foundational astrological text of the Western tradition, the geography, the optics, and the harmonics, constitutes the most comprehensive and most systematically organized body of scientific writing to survive from the ancient world, exercised through the longevity and authority of his works, a more sustained and more comprehensive influence on the subsequent development of Western and Islamic scientific thought than any other ancient author, and his specific contribution to the naming and cataloguing of the stars. Embedded in the star catalogue that constitutes books VII and VIII of the Almagest, has left a direct and identifiable legacy in the nomenclature of the modern sky. The star catalogue of the Almagest, listing 1,022 stars organized into 48 constellations, with each star's position given in ecliptic coordinates and its brightness classified on a 6-magnitude scale that became the standard system for expressing stellar brightness until the quantitative photometric scale of the 19th century replaced it, is the primary source of the constellation system used in the Western astronomical tradition from Ptolemy's time to the present. And the specific descriptions of the individual stars within each constellation, the bright star on the right shoulder of Orion, the star at the tip of the tail of the Great Bear, became the basis of the Arabic star names that Islamic astronomers assigned to the individual stars of the Ptolemaic catalogue, and that survive, in often heavily corrupted transliterated forms, as the proper names of the bright stars in the modern sky. Rigel, Betelgeuse, Aldebaran, Deneb, Altair Vega, Fomalhaut, these Arabic names, applied to the stars of Ptolemy's catalogue by the Islamic astronomers who were their primary users for nearly a millennium, are the specific linguistic residue of the specific synthesis of Greek and Islamic astronomical culture, whose combined legacy constitutes the living heritage of the ancient sky. Fact 55. Ancient comets, fire in the sky, fear in the heart. Comets, the small bodies of ice, dust, and rock that orbit the sun in highly elongated paths, becoming visible as they approach the inner solar system, and the solar heat vaporizes their icy surfaces to produce the bright coma and the characteristic tail that have made them among the most visually dramatic and most culturally impactful of all celestial phenomena, were observed, recorded, and interpreted by virtually every ancient civilization that maintained any systematic attention to the sky, and were almost universally regarded as omens of the gravest significance. Harbingers of disaster, death, war, famine, or the fall of kings and empires, whose specific appearance in the sky was understood not as a natural phenomenon subject to predictable physical laws, but as a deliberate communication from the divine powers that govern the cosmos, a specific message addressed to the human world whose content it was the responsibility of the astronomer priests to interpret and report to the rulers whose fates the omens concerned. The specific interpretation of comets as omens was not, in most ancient cultures, a matter of simple superstition, but a specific application of the more general principle that organized the entire relationship between ancient astronomy and ancient religion. The principle that the celestial bodies were divine, or were governed by divine powers whose specific communications to the human world were encoded in the appearances and motions of those bodies. And that the specific responsibility of the specialist sky watchers was to read those communications with sufficient accuracy and sufficient timeliness to allow the rulers and communities they served to take whatever protective or propitiatory action the omen required. The most extensively documented ancient comet observation is the record of Halley's Comet, the bright periodic comet whose orbital period of approximately 76 years brings it back to the inner solar system with sufficient regularity to have been observed and recorded at every return since at least 240 BCE, the date of the first unambiguous Chinese record of its appearance. The specific identification of the regular returns of Halley's Comet in the historical record, made retrospectively by the astronomer Edmund Halley in 1705, when he recognized that the comets of 1531, 1607, and 1682 were the same object returning on a regular schedule, was one of the great achievements of early modern astronomy. Transforming in a single stroke the most feared of all celestial omens into a precisely predictable natural phenomenon whose next return could be calculated in advance. Fact 56. The astronomical knowledge of ancient Africa beyond Egypt. The astronomical traditions of the African continent south of the Sahara, the specific bodies of sky knowledge developed by the diverse Iron Age and pre-Iron Age cultures of sub-Saharan Africa, most of which maintain no written records and whose astronomical knowledge was therefore transmitted through oral tradition, architectural alignment, and material culture rather than through the clay tablets, papyri, and manuscripts that preserve the astronomical knowledge of the literate ancient civilizations. have received far less scholarly attention than their intrinsic significance deserves, and their partial recovery through the collaborative work of archaeoastronomers and ethnographers with the living custodians of these traditions has revealed a diversity and a sophistication of sky knowledge that challenges the persistent assumption that systematic astronomical observation was the exclusive preserve of the great literate civilizations of the ancient world. The most thoroughly investigated ancient astronomical site in sub-Saharan Africa is the megalithic calendar site of Namaratunga, a group of 19 basalt pillars erected on the western shore of Lake Turkana in northwestern Kenya during the Iron Age period, approximately 300 BCE, whose specific orientations, analyzed by the archaeoastronomer B.M. Lynch and the anthropologist L.H. Robbins in a 1978 paper in the journal Science, were found to correspond to the rising positions of 7 specific stars and constellations used in the traditional Cushitic lunistellar calendar, still employed by the Borana people of Ethiopia and Kenya for the precise timing of ritual and agricultural activities. The Borana calendar, a sophisticated lunar calendar regulated by the observation of specific stars and constellations, whose heliacal risings and settings mark the lunar months with greater precision than the moon's phase alone can provide, is one of the most complex and most precisely documented traditional astronomical systems in Africa. And its specific correspondence with the orientations of the Namaratunga pillars suggests that the astronomical knowledge it encodes has been continuously maintained in the communities of the Lake Turkana region for approximately 2,500 years. Fact 57. Ancient timekeeping, from sundials to water clocks. The specific problem of timekeeping, the measurement of intervals of time shorter than a day with sufficient precision to be practically useful for the scheduling of daily activities, the coordination of social and religious events, and the conduct of astronomical observations, occupied the inventors and craftsmen of the ancient world with an ingenuity and a persistence that produced, over the span of 3 millennia, a remarkable diversity of timekeeping devices whose specific working principles exploited different physical phenomena, but shared the common characteristic of dividing the continuously flowing river of time into measurable intervals, whose relationship to the astronomical cycles that define the day, the month, and the year could be established and maintained. The oldest and simplest time measurement instrument is the gnomon, the vertical stick or post whose shadow, cast by the sun on a flat surface, changes both its length and its direction over the course of the day in a specific pattern determined by the time of year and the observer's latitude, providing a direct visual record of the sun's position in the sky and therefore of the time of day. The gnomon is the conceptual ancestor of the sundial, the more elaborate version in which the shadow-casting element is oriented parallel to the Earth's rotational axis rather than vertically, producing a shadow whose rotational speed is constant throughout the year rather than varying with the season. Sundials of various designs were used throughout the ancient Mediterranean, Near Eastern and Chinese worlds from at least the 2nd millennium BCE, and their specific variety, horizontal, vertical, hemispherical, and anelmatic designs, each optimized for different practical and observational purposes, reflects the substantial investment of mathematical ingenuity that the practical problem of solar timekeeping attracted from ancient mathematicians. The water clock, the clepsydra, in which time is measured by the flow of water from one vessel to another at a controlled rate, addressed the specific limitation of the sundial that it was usable only when the sun was visible, providing a time measurement instrument capable of operating at night, in cloudy weather and indoors, and whose specific use by Babylonian, Egyptian, Greek, and Chinese astronomers for the timing of astronomical observations made it one of the essential tools of ancient observational astronomy. Fact 58. The astronomical traditions of ancient Mesoamerica beyond the Maya, Aztec, and Olmec skis. The astronomical knowledge of the pre-Columbian cultures of Mesoamerica extends considerably beyond the Maya civilization, whose Dresden Codex and elaborate calendar system have received the most extensive scholarly attention, encompassing the specific astronomical traditions of the Aztec Empire, whose massive sacrificial calendar, urban planning, and temple orientation incorporated astronomical alignments of considerable precision. The Olmec culture, whose specific sky knowledge was the likely ancestor of many Mesoamerican astronomical traditions, and the Zapotec and Mixtec civilizations, whose own astronomical and calendrical systems contributed specific elements to the complex web of sky knowledge that characterized the entire Mesoamerican cultural sphere from at least the 1st millennium BCE. The astronomical traditions of the Aztec Empire, the Mexica state that dominated central Mexico from approximately 1428 CE until the Spanish conquest of 1521 CE, were embedded in a cosmological framework of unusual complexity and unusual violence, in which the sun was identified as a deity requiring constant ritual sustenance in the form of human blood and human hearts to maintain its daily journey across the sky. And whose specific consequence, the institutionalized practice of large-scale human sacrifice, whose specific scale shocked the Spanish conquistadors, was directly connected to the astronomical observation of the sun's cycles and the specific fear that the sun might fail to complete its journey if the ritual sustenance was withheld. The great Aztec sun stone, the massive circular basalt carving of approximately 3.5 meters diameter, discovered beneath the central plaza of Mexico City in 1790, and initially misidentified as a calendar, but now understood primarily as a cosmological monument representing the Aztec understanding of the structure of the cosmos and the history of the successive world ages, is the most visually impressive single artifact produced by Mesoamerican astronomical and cosmological knowledge. Its specific iconographic content, encoding the Aztec cosmological tradition in a form whose particular density of meaning has been the subject of intensive scholarly study since its recovery. Fact 59. How ancient astronomers measured angles, the technology of precision. The specific challenge of measuring angles, determining with precision the angular separation between two celestial objects, or the angular altitude of a star or planet above the horizon, or the angular diameter of the sun or moon, was the fundamental technical problem of ancient observational astronomy, the measurement whose accuracy ultimately determined the quality of every astronomical model, every star catalogue, and every calendar system that ancient astronomers produced. And whose progressive improvement, through the development of increasingly sophisticated measuring instruments and observational techniques, constitutes the specific technological history of ancient astronomy in its most concrete and most consequential dimension. The oldest and simplest angle measuring technique was the direct comparison of observed positions with reference points on the horizon or with other celestial objects whose positions were known, a technique that required no instruments beyond the human eye and the natural landmarks of the horizon, but whose specific accuracy was limited by the precision with which the naked eye could estimate angular separations and by the quality of the reference points available. The gnomon, discussed in the previous fact as a timekeeping device, was also the primary instrument for measuring the altitude of the sun, the fundamental observation from which the length of the year and the specific parameters of the solar orbit were determined. By measuring the length of the gnomon's shadow at noon on different dates throughout the year and knowing the height of the gnomon, an ancient astronomer could calculate the noon altitude of the sun on any day with a precision limited primarily by the accuracy of the shadow length measurement. The most significant ancient instrument for precision angle measurement was the large meridian instrument, the fixed quadrant or sextant oriented precisely in the plane of the meridian, whose specific advantage over portable instruments was that its large scale allowed the arc to be graduated in finer divisions, achieving angular measurement precision approaching 1 arc minute in the best examples, compared to the several arc minutes achievable with the best portable instruments. Fact 60. Ancient astronomy at 60. 40 facts from the summit. 60 facts into the story of ancient astronomy, and the vast geography of ancient sky knowledge has been traversed in its broad outlines, from the Ice Age bone notches of the Lebombo to the precision stone instruments of Ulugh Beg Samarkand, from the navigational star compass of the Polynesian voyagers to the dark emu constellation of Aboriginal Australia, from the eclipse prediction Saros cycle of the Babylonians to the Venus tables of the Maya Dresden Codex. We have understood that every ancient civilization that looked up at the sky brought to what it saw a specific combination of practical need, mathematical capacity, and cultural meaning that shaped the specific form its astronomical knowledge took, and that the diversity of those forms, the extraordinary variety of ways in which human beings have organized and expressed their understanding of the sky, is as remarkable and as revealing as the specific discoveries that each tradition made. We have understood that the Antikythera mechanism, a bronze computer of 30 gears built in the 2nd century BCE to track the sun, moon, planets, and eclipse cycles, exists, that it was made by human hands in the ancient world, and that its existence means we do not know as much about the technological capabilities of the ancient world as we sometimes assume. 40 facts remain. They will carry us through the specific stories, the specific places, and the specific moments where ancient human beings and the ancient sky met most dramatically and most productively, and through the question that the entire history of ancient astronomy ultimately poses. What was it that the sky gave to every civilization that studied it, and what would those civilizations have been without it? This is explored during sleeping. Fact 61. The astronomical significance of Angkor Wat, a temple aligned with the cosmos. Angkor Wat, the vast temple complex constructed in the early 12th century CE by the Khmer king Suryavarman II in the capital of the Khmer Empire, in what is now northwestern Cambodia, covering approximately 1.6 square kilometers of built structure within an outer enclosure of approximately 200 hectares, and constituting the largest religious monument ever constructed by any civilization, embeds within its specific architectural layout. Its precise cardinal orientations, and the specific proportions of its spatial organization, a set of astronomical references, whose particular depth and precision have been extensively documented by the archaeoastronomer Elena Manica in her detailed study of the monument's measurements and their relationship to Hindu cosmological and calendrical systems. The specific astronomical dimension of Angkor Wat's design begins with its cardinal orientation. The temple complex faces west rather than east, an unusual orientation that has been explained by its funerary significance, and that aligns the central axis of the monument with the setting sun at the equinoxes, creating a specific visual effect on the equinox evenings when the sun descends along the western causeway and sets precisely behind the central tower as seen from the main entrance gate. The specific measurements of the monument's galleries, causeways, and chambers, analyzed by Manica in terms of the Khmer unit of measurement called the hat, yield numerical values corresponding to significant astronomical periods: the length of the solar year, the length of the lunar month, the length of specific planetary cycles. Embedded in the architecture with a precision that she argues reflects a deliberate intent to make the temple a physical expression of the Hindu cosmological system, in which space and time, the dimensions of the universe and the cycles of its celestial bodies, are unified in a single mathematical framework. The specific visual astronomical effects at Angkor Wat, the equinox sunset alignment along the western causeway, the summer solstice sunrise alignment over the central tower, as seen from a specific location on the western causeway, have been confirmed by independent astronomical analysis and represent some of the most dramatic architectural expressions of astronomical knowledge in the entire ancient and medieval world. Fact 62. The ancient Greek measurement of the moon's distance. The measurement of the distance from the Earth to the moon, one of the fundamental quantities of the astronomical universe, the specific number that anchors the scale of the entire solar system, and without whose knowledge no physically meaningful model of the cosmos can be constructed, was first achieved with reasonable accuracy by the Greek astronomer Hipparchus in the 2nd century BCE. Using a method based on the geometry of solar eclipses, whose specific elegance and specific limitation illustrate with particular clarity both the power and the constraint of ancient Greek astronomical methods. The specific method Hipparchus used began with the observation of a solar eclipse that was total at one location, the Hellespont, according to his account, and merely partial at another location, Alexandria, where approximately 4/5 of the sun's disk was covered. The difference in the eclipse fraction between the two locations provided a measure of the shift in the moon's apparent position, as seen from 2 points on the Earth's surface, separated by a known distance, a shift called the lunar parallax, whose specific value is inversely proportional to the moon's distance. By combining the measured eclipse difference with the known distance between the Hellespont and Alexandria, expressed as a fraction of the Earth's circumference using Eratosthenes' measurement, Hipparchus was able to calculate the moon's distance in units of the Earth's radius, obtaining a value between 59 and 67 Earth radii for the moon's minimum and maximum distances in an eccentric orbit. Compared to the modern values of approximately 56.4 and 63.8 Earth radii. The specific accuracy of Hipparchus's measurement, achieved without any instrument capable of measuring angular positions to better than a few arcminutes, using only the geometric relationship between a solar eclipse seen from two different locations, was the result of an extraordinarily clever exploitation of the specific geometry of the eclipse situation. Turning a qualitative astronomical event into a quantitative measurement of cosmic distance, with a precision that required nothing more than careful observation and the correct application of elementary geometry. Fact 63. The Saros cycle, predicting eclipses across millennia. The Saros cycle, the period of approximately 6,585.3 days, equivalent to approximately 18 years, 11 days, and 8 hours, after which the relative positions of the Sun, Moon, and Earth return to a configuration so nearly identical to a previous one that the sequence of eclipses, both solar and lunar, repeats with high fidelity. Each eclipse in the new cycle, occurring approximately 8 hours later in the day, and approximately 120 degrees of longitude further west than the corresponding eclipse in the previous cycle. is one of the most remarkable numerical coincidences in the mechanics of the solar system and the specific astronomical relationship, whose discovery by Babylonian astronomers from their accumulated eclipse records represents perhaps the greatest achievement of ancient observational science. The specific reason the Saros cycle works is the near-exact numerical relationship between three independent astronomical periods. Synodic month, the period from new moon to new moon, approximately 29.5306 days; the anomalistic month, the period from perigee to perigee, the cycle of the moon's varying distance from the Earth that determines whether solar eclipse will be total or annular; and the draconic month, the period between successive crossings of the moon's orbit across the plane of the Earth's orbit, which determines whether new or full moon will produce an eclipse at all. The Saros cycle corresponds almost exactly to 223 synodic months, 239 anomalistic months, and 242 draconic months, three different astronomical periods that are nearly in the ratio 223, 239, 242, a numerical coincidence whose probability of occurring by chance in any randomly constructed planetary system is very low, and whose specific occurrence in our solar system is ultimately a consequence of the gravitational interactions that have shaped the moon's orbit over the history of the Earth-Moon system. The Babylonian astronomers who identified the Saros cycle did not know the physical reason for its existence. The theory of gravitation that explains it would not be formulated for 2,000 years, but their empirical identification of the pattern from observational records was itself a remarkable achievement, requiring the maintenance of consistent, accurate eclipse records over a period long enough for the cycle's repetitive character to become apparent. Fact 64: the ancient Roman calendar, the astronomical mess that Caesar fixed. The Roman calendar in the centuries before Julius Caesar's reform, the traditional calendar of 10 months that Romulus was said to have instituted, and that was expanded to 12 months by his successor Numa Pompilius, a lunar calendar of 355 days, whose specific divergence from the solar year of 365.25 days required the periodic insertion of an intercalary month to keep it in alignment with the seasons, was, by the time of Julius Caesar's consulship in the middle of the 1st century BCE, in a state of such profound disorder that the calendar bore almost no relationship to the actual astronomical seasons, the civic year having drifted months out of alignment with the solar year through a combination of neglected intercalations, politically motivated calendar manipulations by the pontiffs who were responsible for declaring intercalary months, and the general disruption of civic administration during the decades of civil war that preceded Caesar's assumption of supreme power. The specific magnitude of the misalignment between the Roman calendar and the astronomical year at the time of Caesar's reform, the calendar year beginning in what was astronomically the autumn rather than the spring, the Roman harvest festivals occurring in what was actually early summer, was sufficient to require a correction of approximately 90 days in a single year, producing the year 46 BCE, known as the Year of Confusion, which was given 445 days to reset the calendar to its correct relationship with the sun. Caesar's reformed calendar, the Julian calendar, designed with the assistance of the Egyptian astronomer Sosigenes of Alexandria, and based on the Egyptian civil calendar, whose solar basis and specific management of the extra quarter day per year through a quadrennial intercalary day Caesar adapted for Roman use, was a genuine astronomical improvement over its predecessor. Abandoning the lunar basis of the traditional Roman calendar, entirely in favor of a purely solar year of 365 days, with a leap day added every 4 years, and reducing the annual calendar error from the multiple days of the lunar system to the approximately 11 minutes by which the Julian year of 365.25 days exceeds the actual solar year of 365.2422 days. Fact 65: ancient observatory architecture, buildings that were instruments. The specific tradition of designing buildings whose architecture incorporated astronomical alignments, whose doorways, windows, corridors, or entire orientations were positioned to admit light from the sun, moon, or specific stars at specific astronomically significant moments of the year, was not limited to the prehistoric megalithic monuments of Europe and the monumental temples of Egypt and Mesoamerica, but extended in various forms through the ancient and medieval worlds of Asia, the Islamic world, and pre-Columbian America, reflecting the specific understanding that the most precise and most reproducible astronomical observations were those made at a fixed site with a fixed architectural reference, whose specific geometry transformed the building itself into an observing instrument of permanent character. The most architecturally refined ancient observatory in Asia is the Cheomseongdi, the stone astronomical observatory tower constructed in the capital of the Silla Kingdom, in what is now Jeonju in South Korea in approximately 634 CE, during the reign of Queen Seondeok, whose specific cylindrical form, approximately 9 meters high with a square base and a specific arrangement of stone courses, has been interpreted by various researchers as incorporating astronomical symbolism. The 362 stones in the body of the tower corresponding to the days of the lunar year, the 12 courses below and above the central window corresponding to the 12 months, though the specific function of the structure as a practical astronomical observation platform versus its role as an astronomical monument of symbolic character remains debated. In the Islamic world, the specific tradition of mosque orientation toward Mecca, the Qibla direction required for the proper performance of the 5 daily prayers, drove the development of mathematical methods for determining the astronomical azimuth of any distant location from any other location on the Earth's spherical surface. A problem in spherical trigonometry, whose solution required the specific mathematical tools that Islamic mathematicians developed, and which in turn advanced the broader mathematical astronomy of the period in ways that extended well beyond the practical problem of mosque orientation that originally motivated them. Fact 66. The astronomical knowledge of ancient Mesopotamia before Babylon, the Sumerians, and the sky. The astronomical knowledge of ancient Mesopotamia in its earliest phases, the sky observations and celestial traditions of the Sumerian city-states of the 3rd millennium BCE, the world's first urban civilization, whose specific astronomical achievements in the period before the Babylonian dynasty are partially recoverable from the astronomical content of the earliest cuneiform texts and from the astronomical references embedded in Sumerian mythology and religious literature, constitutes the deepest recoverable layer of the systematic skywatching tradition whose products, the Babylonian star catalogues and predictive tables, were discussed in earlier facts, and whose specific character in this early period reflects the specific concerns of a civilization whose entire agricultural and economic system was organized around the flooding and recession of the Tigris and Euphrates rivers, and whose sky knowledge was therefore shaped above all by the need to predict and time these hydrological events in relation to the celestial calendar. The Sumerians developed, in the 3rd millennium BCE, the sexagesimal number system, the base 60 notation that they applied to both commercial accounting and astronomical calculation, and whose specific mathematical properties, including the large number of exact divisors of 60, made it particularly convenient for the expression of fractions and for the specific kinds of astronomical calculations that the Babylonians would later develop into a comprehensive mathematical astronomy. The legacy of the Sumerian sexagesimal system in the modern world is pervasive and intimate. The specific division of the circle into 360 degrees, of the degree into 60 arcminutes, and of the arcminute into 60 arcseconds, the angular measurement system used by every astronomer and navigator on Earth today, is a direct inheritance from the Sumerian mathematical tradition, as is the specific division of the hour into 60 minutes and the minute into 60 seconds that governs every clock and every calendar on the planet. Every time a modern astronomer specifies the position of a star in degrees, arcminutes, and arcseconds, they are using a mathematical notation invented by the astronomers of ancient Sumer more than 4,000 years ago. Fact 67. The astronomical myths of ancient Greece, stories that map the sky. The mythology of ancient Greece, the vast and internally complex body of stories about gods, heroes, monsters, and the origins of the world that constitutes the most extensively documented mythological tradition of the ancient Mediterranean world, is so thoroughly saturated with astronomical content that a comprehensive astronomical commentary on the Greek myths would constitute a substantial portion of the total mythological corpus. Reflecting the specific degree to which the Greek religious and cultural imagination used the sky as a canvas on which to project the stories that expressed its deepest values and its most fundamental anxieties. The specific mechanism by which astronomical content entered Greek mythology was the katasterism, the transformation of a mythological figure into a constellation or star, typically as the final act of a story, whose earlier episodes provided the specific narrative context that explained the figure's presence in the sky and the specific constellation whose stars marked their position. The myths of the major constellations, Orion the hunter placed in the sky with his dogs Canis Major and Canis Minor and his prey the hare, facing the charging Taurus the bull, and threatened by the rising Scorpius the scorpion, Perseus carrying the severed head of the Medusa and rescuing the chained Andromeda from the sea monster Cetus. The twin heroes Castor and Pollux sharing immortality and the sky as Gemini are not merely decorative stories attached to arbitrary star patterns, but specific mythological narratives whose astronomical content serve practical mnemonic functions. Encoding in memorable story form the specific positions and relative locations of the constellations that an ancient Greek navigator, farmer, or priest needed to identify in the night sky. The specific relationship between the constellation positions and the mythological narratives, Orion's seasonal conflict, with the Scorpion expressed in the fact that Orion sets in the west as Scorpius rises in the east, the two never sharing the sky simultaneously, represents a specific level of astronomical sophistication embedded in the mythological tradition, transforming what might appear to be simple stories into a sophisticated mnemonic system for the navigation of the night sky. Fact 68. The astronomical traditions of ancient Japan, heaven, and the imperial court. The astronomical tradition of ancient and medieval Japan, the specific body of sky knowledge developed and maintained by the Japanese imperial court from the introduction of Chinese astronomical methods in the late 6th century CE through the gradual development of an independent Japanese astronomical tradition in the following centuries, was shaped from its beginnings by the specific political and religious framework of the Japanese imperial system, in which the emperor was understood as the direct descendant of the sun goddess Amaterasu, and the specific movements of the celestial bodies were therefore interpreted as communications from the imperial ancestors, whose proper reading was the specific responsibility of the court astronomers. The introduction of systematic astronomical observation to Japan was closely associated with the broader introduction of Chinese culture, writing, and Buddhism in the late 6th and early 7th centuries CE, when Japanese embassies to the Sui and Tang courts of China returned with astronomers, calendar specialists, and astronomical texts whose specific knowledge was adopted and adapted by the Japanese court to meet the specific needs of a society that was simultaneously absorbing Chinese cultural forms and developing its own distinctive institutional structures. Japanese record of the 1054 supernova, preserved in the diary of the Fujiwara regent Fujiwara no Sadeya, written several centuries after the event, but apparently based on earlier records, is one of the three primary historical sources for this event, alongside the Chinese imperial records and the accounts in Arab astronomical texts, and its specific content, describing the appearance of a guest star of great brightness in the constellation corresponding to Taurus, provides independent confirmation of the Chinese observation and of the specific astronomical event's exceptional character. The specific calendar reform undertaken by the Japanese court in the 8th century CE, the adoption and adaptation of the Chinese lunisolar calendar system for Japanese use, required the specific astronomical calculations of the lengths of the lunar month and the solar year, and the specific intercalation rules needed to keep them in alignment, driving the development of mathematical astronomical capability in the Japanese court that would eventually produce, in the Edo period of the 17th to 19th centuries, an independent Japanese astronomical tradition of considerable sophistication. Fact 69. Ancient astrological traditions, when astronomy and divination were one. The specific relationship between astronomy and astrology in the ancient world, the relationship between the systematic observation and mathematical modeling of the celestial bodies, which constitutes astronomy in the modern sense, and the interpretation of celestial phenomena as omens relevant to human affairs, which constitutes astrology, was not in the ancient period the relationship between a rigorous science and a discredited pseudoscience that the modern perspective imposes on it, but a relationship between two inseparable aspects of a single intellectual enterprise, whose specific unity was not questioned by any ancient culture, and whose separation into distinct disciplines with different epistemic statuses was a product of the specific intellectual transformations of the early modern period, rather than a distinction that any ancient astronomer or astrologer would have recognized. The oldest astrological tradition in the documented historical record is the Babylonian tradition of celestial divination, the interpretation of the appearances of the moon, planets, comets, and unusual celestial phenomena as omens whose specific meanings, codified in the Great Omen series Enuma Anu Enlil, were relevant primarily to the welfare of the king and the state, rather than to the fate of individual persons. The Enuma Anu Enlil, a compilation of approximately 70 tablets containing approximately 7,000 omens, assembled in its canonical form in the 1st millennium BCE, but incorporating material that may be considerably older, is the primary document of Babylonian astral divination and one of the most extensively studied bodies of ancient astronomical and astrological knowledge. Its specific content providing information not only about the astrological interpretations attached to celestial phenomena, but about the observational standards and the specific astronomical knowledge of the Babylonian scholars who compiled it. The transition from this state-focused Babylonian celestial divination to the personal or natal astrology, the interpretation of the configuration of the celestial bodies at the moment of an individual's birth as relevant to that individual's personal fate, occurred in approximately the 5th century BCE, and the specific intellectual apparatus of natal astrology, including the zodiac, the concept of the ascendant, and the system of astrological houses, was developed largely by Greek scholars working in the Hellenistic period under the combined influence of Babylonian omen literature and Greek geometrical astronomy. Fact 70, Ancient Astronomy at 70, 30 Facts from the Stars. 70 facts into the story of ancient astronomy and the full human depth of the subject, the specific ways in which the sky was woven into the fabric of ancient life at every level, from the imperial court astronomy of China and Japan to the navigational star compass of the Pacific Voyager, from the Babylonian eclipse records that identified the Saros cycle to the Aboriginal Australian dark cloud constellations that told a community when the emus were nesting, has become fully and richly apparent. We have understood that the astronomical traditions of the ancient world were not a single tradition with a single history, but a family of related and sometimes interacting traditions, each shaped by the specific environment, the specific needs, and the specific intellectual framework of the civilization that produced it, and each making specific contributions to the accumulated human understanding of the sky that deserve to be recognized on their own terms, rather than only as stepping stones to the astronomy of Copernicus and Newton. We have understood that the specific union of astronomy and astrology in the ancient world was not a failure of intellectual discrimination, but the expression of a specific cosmological worldview in which the boundary between the mathematical description of celestial motions and the interpretation of those motions as meaningful communications from the divine powers governing the cosmos was not a boundary that ancient thinkers drew, and that the specific astronomical precision that the astrological tradition required, the accurate prediction of planetary positions that was necessary for the casting of horoscopes, was one of the primary drivers of astronomical progress in the Babylonian and Hellenistic periods. 30 facts remain. They will carry us to the final and deepest dimensions of this story, the specific legacy of ancient astronomy in the modern world, the specific moments when the ancient sky and the ancient mind met most productively, and the enduring question of what it means that the same stars that guided the first Polynesian canoes across the Pacific and inspired the first Babylonian clay tablet records are the stars that shine above us tonight. This is explored during sleeping. Fact 71, the astronomical legacy of ancient India, 0, infinity, and the stars. The specific mathematical achievements of ancient Indian astronomers, the development of the decimal positional number system with a symbol for 0, the invention of the trigonometric sine function, and its systematic application to astronomical calculation, the development of series approximations for trigonometric functions that anticipate the calculus of Newton and Leibniz by more than a millennium, and the construction of astronomical tables of planetary motion, whose specific accuracy was among the highest achieved in any ancient tradition, represent a contribution to the history of science whose specific importance has been consistently underappreciated in the Western historical tradition, whose specific focus on the Greek and Islamic astronomical lineage has tended to obscure the independent, and in many respects equally impressive achievements of the Indian tradition and its specific role in the transmission of mathematical tools that were essential for the subsequent development of modern science. The Kerala School of Astronomy and Mathematics, the specific intellectual tradition centered in the southern Indian state of Kerala that flourished between approximately the 14th and 16th centuries CE, producing a succession of brilliant mathematicians and astronomers including Madhava of Sangamagrama, Nilakantha Somayaji, and Jayasthadeva, made specific mathematical achievements whose content was not known to European scholars until centuries later, and whose independent discovery in Kerala is a remarkable chapter in the parallel development of mathematical knowledge in different parts of the world. Madhava of Sangamagrama, working in approximately 1400 CE, derived infinite series expansions for the sine, cosine, and arctangent functions. The specific mathematical tools that James Gregory and Gottfried Wilhelm Leibniz are conventionally credited with discovering in Europe in the 17th century, and used them to calculate the value of pi to 11 decimal places, an accuracy not achieved in the European mathematical tradition until after the introduction of calculus. Nilakantha Somayaji, working in approximately 1500 CE, developed a specific astronomical model in which the 5 planets visible to the naked eye orbit the Sun, while the Sun itself orbits the Earth. A geoheliocentric model that represents a specific halfway point between the purely geocentric Ptolemaic system and the fully heliocentric Copernican system. And that anticipates the similar model developed independently by Tycho Brahe in Europe in the late 16th century. Fact 72. The astronomical significance of the pyramids, shafts, stars, and immortality. The specific astronomical dimensions of the Great Pyramids of Giza, beyond the cardinal orientation of the Great Pyramid, whose precision was discussed in an earlier fact, include a set of internal architectural features, whose specific astronomical alignments have been the subject of extensive study and considerable debate, since the Egyptologist Virginia Trimble first proposed in 1964 that the 4 narrow shafts extending from the King's Chamber and Queen's Chamber of the Great Pyramid were oriented towards specific celestial targets, whose astronomical and religious significance was central to the pyramid's funerary function. The shafts of the Great Pyramid, 2 extending from the King's Chamber and 2 from the Queen's Chamber, each approximately 20 to 23 centimeters wide and angled upward from horizontal at specific angles that direct them towards specific regions of the sky, were long assumed to be ventilation channels, a function whose practical necessity in a sealed burial chamber is obvious, but whose adequacy as a complete explanation was questioned by researchers who noted that the shafts are too narrow for effective ventilation, and that their specific orientations, if they were merely ventilation channels, would have been selected for functional rather than astronomical reasons. The astronomical interpretation proposed by Trimble, and subsequently elaborated in detail by the Egyptologist and engineer Robert Bovell, identifies the northern shafts of both chambers as directed toward the circumpolar stars, the stars that never set below the Egyptian horizon and therefore served in the Egyptian religious tradition as symbols of immortality, the eternal stars with which the pharaoh's soul was destined to unite, and the southern shafts as directed towards specific stars of great religious significance. The southern shaft of the King's Chamber toward the belt of Orion, identified in the Egyptian tradition with the god Osiris, and the southern shaft of the Queen's Chamber towards Sirius, identified with the goddess Isis. The specific astronomical targets of these shafts, as calculated from the known precession of the equinoxes, correspond to the positions of these stars at the meridian, as they would have appeared from the pyramid at the time of its construction in approximately 2560 BCE, providing specific astronomical evidence that the shaft orientations were deliberately chosen to align with religiously significant stars in the sky of the Old Kingdom period. Fact 73. The ancient Norse astronomical tradition, stars of the Viking Age. The astronomical knowledge of the Norse peoples, the specific body of sky knowledge developed and maintained by the Scandinavian cultures of the Viking Age, from approximately the 8th to the 11th century CE, and whose particular character reflected the specific needs of a maritime and agricultural society, whose voyages across the North Atlantic to Iceland, Greenland, and eventually North America required navigational capability of the highest order, was shaped above all by the specific demands of oceanic navigation in northern latitudes, where the midnight sun of summer and the polar darkness of winter created observational conditions profoundly different from those of the Mediterranean and Middle Eastern astronomical traditions, whose records have dominated the history of ancient astronomy. The specific navigational astronomy of the Viking Age seafarers encompassed the use of the pole star for latitude determination, the direct measurement of the altitude of Polaris above the northern horizon, providing a direct reading of the observer's latitude, a technique of great simplicity and great reliability in the high northern latitudes where the Norse voyaged, combined with the use of the sun's altitude at noon for latitude determination during the summer months when the sun was visible at midnight and Polaris could not be used because the sky never darkened. The specific Norse navigational instrument, whose existence and function has been most debated by historians, is the solar compass, a device whose specific design has been reconstructed from a fragmentary wooden object recovered from an 11th century Norse settlement in Greenland and whose particular function, the determination of compass direction from the shadow cast by a central pin on a marked wooden disc, would have allowed Norse navigators to determine their heading relative to the sun at any time of day, compensating for the variation in the sun's azimuth throughout the day that makes direct solar navigation without such compensation unreliable. The specific Norse mythological framework for understanding the sky, the cosmological structure of the 9 worlds connected by the world tree Yggdrasil, the specific identification of the Milky Way as Bifrost, the rainbow bridge connecting the human world to Asgard, and the specific characters of the Norse sky gods. Reflects a cosmological imagination of considerable richness, whose specific relationship to the practical navigational astronomy of the Viking Age seafarers remains partially understood and richly suggestive. Fact 74. Ancient star names, the Arabic layer of the modern sky. The proper names by which the bright stars of the modern sky are known, the names that appear on star charts, in planetarium programs, and in the descriptions of every astronomy guide available to the modern reader, are, with very few exceptions, Arabic names applied to the stars of the Ptolemaic catalogue by Islamic astronomers between the 9th and 15th centuries CE. Preserved through centuries of use in Arabic astronomical tables, and eventually transmitted into the European astronomical tradition through the specific channel of the Latin translations of Arabic astronomical texts that constituted the primary vehicle of Islamic scientific knowledge into medieval Europe. The specific character of the Arabic star names reflects the specific way in which Islamic astronomers engaged with the Ptolemaic star catalogue. Each star in the catalogue was identified by Ptolemy with a description of its position within its constellation. And these descriptions were translated into Arabic either directly or with the addition of the Arabic name for the relevant constellation, producing names whose specific etymology, when recoverable, typically refers to the star's position in the figure of the constellation. Betelgeuse, the bright red star marking the right shoulder of Orion, derives from the Arabic Yad al-Jawza, meaning the hand of the giant, the Jawza being the Arabic name for the Orion constellation, whose specific meaning is debated, but may originally have referred to a walnut tree before being applied to Orion. Rigel, the brilliant blue-white star at Orion's left foot, derives from the Arabic Rail al-Jawza al-Yusra, meaning the left leg of the giant, contracted through centuries of use. Aldebaran, the red giant star marking the eye of Taurus the bull, derives from the Arabic Aldabaran, meaning the follower, a name referring to the star's position following the Pleiades cluster as the sky rotates. Deneb, the brilliant star marking the tail of Cygnus the swan, derives from the Arabic Danab al-Dajaja, the tail of the hen. Vega, the brightest star in Lyra, derives from the Arabic al-Nasr al-Waki, the swooping eagle, reflecting an Arabic constellation figure that identified the same stars as a swooping bird rather than the Greek lyre. Fact 75. The ancient measurement of the year, how long is a year? The specific astronomical problem of determining the precise length of the year, the interval of time that must elapse between successive vernal equinoxes, or between successive winter solstices, or between successive heliacal risings of a specific star, for the calendar to remain accurately aligned with the seasons, was one of the most practically important and most persistently challenging problems of ancient astronomy. Requiring the measurement of a time interval long enough that the accumulated observational errors of a single year's measurements were smaller than the precision sought, and therefore demanding either the construction of instruments of exceptional precision or the comparison of observations separated by decades or centuries to average out the random errors of individual measurements. The specific strategies that different ancient astronomical traditions developed to address this challenge reflect both the specific institutional frameworks within which their astronomy was practiced and the specific mathematical tools available to them. The Babylonian approach was fundamentally empirical. The long series of systematic observations maintained in the astronomical diaries provided, over sufficient time, a statistical baseline from which the length of the year could be extracted by identifying the specific date of the vernal equinox in a large number of successive years and fitting a period to the observed sequence of dates. The Greek approach was more geometric. The comparison of the specific positions of the sun relative to the stars, measured with increasing precision by successive astronomers, allowed the determination of the tropical year's length with an accuracy limited primarily by the precision of the positional measurements rather than by the number of years observed. Hipparchus's determination of the tropical year, approximately 365.25 days minus approximately 1/300th of a day, corresponding to approximately 365.2467 days, was the most accurate ancient value, differing from the modern value of 365.2422 days by only approximately 4.5 minutes. An accuracy achieved by comparing his own observation of the autumnal equinox with an observation made by Aristarchus approximately 145 years earlier, and averaging the accumulated error of 145 years of calendar drift over the full interval to obtain a very precise annual figure. Fact 76. The astronomical knowledge of the ancient Celts, Druids, and the sky. The astronomical knowledge of the ancient Celtic peoples, the Iron Age and early medieval cultures that occupied large parts of Western and Central Europe from approximately the 8th century BCE onward, and whose specific sky knowledge, embedded in a religious and calendrical tradition maintained by the specialist priestly class known as the Druids, has been the subject of considerable scholarly speculation and considerable popular elaboration since the classical Greek and Roman sources that provide the primary written evidence of Druidic practice describe the Druids as skilled astronomers and natural philosophers, is among the most difficult of all ancient astronomical traditions to reconstruct, because the Druids maintained a strict prohibition on the writing down of their knowledge, transmitting everything in the oral tradition of extended poetic memorization that the classical sources report required up to 20 years of study, and whose specific astronomical content perished with the suppression of the Druidic order under Roman rule and the subsequent conversion of the Celtic peoples to Christianity. The specific evidence for Celtic astronomical knowledge is therefore primarily archaeological. The orientations of Celtic ritual sites, the specific positions and alignments of the Latine period oppida and shrines that constitute the primary physical record of Celtic religious practice, and the survival in the medieval Irish and Welsh literary traditions of mythological and calendrical content that may preserve echoes of older astronomical knowledge, informs too transformed by centuries of oral transmission and literary reworking to be easily read as direct astronomical evidence. The Coligny calendar, the large bronze plate inscribed with a Gaulish language calendar, discovered near Bourg-en-Bresse in France in 1897 and dated to approximately the 2nd century CE, is the most direct surviving document of ancient Celtic calendrical astronomy, preserving a 5-year cycle of 62 lunar months with specific intercalation rules for maintaining the calendar's alignment with the solar year, and whose specific structure demonstrates a sophisticated understanding of the relationship between the lunar and solar cycles comparable to the calendrical knowledge of other contemporary ancient astronomical traditions. Fact 77. The ancient astronomical tradition of Mesopotamia, the planets as gods. The specific religious and mythological significance assigned to the 5 planets visible to the naked eye, Mercury, Venus, Mars, Jupiter, and Saturn, by the astronomers and priests of ancient Mesopotamia, and whose particular identification of each planet with a specific major deity of the Babylonian pantheon constitutes one of the oldest and most persistent layers of astronomical symbolism in the entire Western cultural tradition, represents the specific point at which the observational astronomy of ancient Mesopotamia and the mythological and religious tradition of the same civilization were most intimately fused, producing a system of celestial symbolism whose specific assignments: Jupiter as Marduk, the king of the gods; Venus as Ishtar, the goddess of love and war; Mars as Nergal, the god of death and pestilence; Saturn as Ninurta, the god of agriculture and the plough; Mercury as Nabu, the god of writing and wisdom, have survived in continuously modified but fundamentally consistent forms through 2,500 years of subsequent astronomical and astrological tradition, from the Babylonian omen literature through the Greek and Roman periods, whose specific translations of the Babylonian divine identifications into Greek and Roman equivalents: Ares for Nergal, Aphrodite for Ishtar, Kronos for Ninurta, Hermes for Nabu. Zeus for Marduk established the planetary mythology of the classical world that passed in turn into the Latin planetary names Mars, Venus, Saturn, Mercury, Jupiter, that every language of European origin uses today. The specific days of the week, whose names in English preserve a mixture of the Latin planetary tradition and its Norse mythological equivalent: Sunday for the sun, Monday for the moon, Tuesday for Tiaoth, the Norse equivalent of Mars, Wednesday for Woden, the Norse equivalent of Mercury, Thursday for Thor, the Norse equivalent of Jupiter, Friday for Frigg, the Norse equivalent of Venus, Saturday for Saturn, are the most intimate and most continuously present legacy of the Babylonian planetary theology in modern daily life, a specific inheritance from the skywatching priests of ancient Mesopotamia that enters the consciousness of every person in the modern world every time they write or speak a date. Fact 78. Ancient astronomical instruments of the Americas, observatories without telescopes. The astronomical observation sites and instruments of the pre-Columbian Americas, the specific structures, alignments, and architectural features whose particular design reflects the specific astronomical knowledge and observational practices of the indigenous civilizations of North, Central, and South America, represent a body of archaeoastronomical evidence whose systematic investigation has revealed, in the past half-century of research, a depth and sophistication of ancient American astronomical knowledge that challenges the persistent assumption that the great astronomical traditions of the ancient world were confined to the civilizations of the Old World, and that the astronomers of the Americas were working with less precision and less mathematical sophistication than their Babylonian, Greek, and Islamic counterparts. The most thoroughly investigated ancient American astronomical structure is the caracol at Chichen Itza, the cylindrical stone tower constructed by the Maya in approximately 900 CE on the Yucatan Peninsula of Mexico, whose name means snail in Spanish and refers to the internal spiral staircase of the tower, and whose specific architectural features, the specific orientations of its windows, doorways, and the walls of the platform on which it stands, have been analyzed by archaeoastronomers Anthony Aveni and Sharon Gibbs as incorporating a set of astronomical alignments focused primarily on the extreme positions of Venus, whose specific rising and setting points on the horizon at the northern and southern limits of its annual excursion were marked by the specific orientations of the tower's windows with a precision that required careful observational work over extended periods. In North America, the most extensively studied ancient astronomical site is the Bighorn Medicine Wheel, a circular stone structure approximately 28 meters in diameter, constructed on a high mountain summit in Wyoming by the indigenous peoples of the Great Plains, whose specific spoke-like arrangement of cairns, radiating from a central hub, has been found to incorporate alignments toward the summer solstice sunrise, the heliacal risings of several bright stars including Aldebaran, Rigel, and Sirius, and the setting point of the summer solstice sun, creating a sky-marking structure of considerable astronomical sophistication in one of the most remote and most physically demanding environments in which any ancient people chose to conduct systematic astronomical observation. Fact 79. The astronomical traditions of ancient Persia, the royal stars. The four royal stars of ancient Persian astronomy, the specific four bright stars whose particular positions, approximately equally spaced around the sky, and approximately marking the positions of the sun at the solstices and equinoxes during the epoch when the Persian astronomical tradition was formalized, identified them as the guardians of the four cardinal directions and the four seasons, and whose specific astrological significance as the most powerful stellar omens in the entire sky was transmitted from the Persian tradition through Babylonian and Greek astronomy into the medieval Western and Islamic astrological traditions, where it remains one of the most consistently recognized groups of stars. Represent one of the most specific and most historically traceable examples of the transmission of a specific astronomical concept from one ancient civilization to the next across the full span of the Western astronomical tradition. The four royal stars are Aldebaran in Taurus, the guardian of the East, the watcher of the East, associated with the vernal equinox during the period when the Persian tradition was formalized, Regulus in Leo, the guardian of the North, sometimes called the heart of the lion and the royal star par excellence, associated with the summer solstice, Antares in Scorpius, the guardian of the West, whose specific name in Greek means rival of Mars, reflecting the specific reddish color it shares with the planet Mars, associated with the autumnal equinox, and Fomalhaut in Piscis Austrinus, the guardian of the South, the solitary one, the bright star of the southern sky visible in autumn and associated with the winter solstice. The specific identification of these four stars as a special group, as the royal stars, the watchers, the guardians, dates to at least the 2nd millennium BCE in the Babylonian tradition, and was adopted and elaborated by the Persian Zoroastrian astronomical tradition, in which the four stars were identified with the four divine beings called Yazatas, whose specific cosmic responsibility was the guardianship of the four cardinal directions and the maintenance of the celestial order. Fact 80. Ancient astronomy at 80. 20 facts from the final stars. 80 facts into the story of ancient astronomy, and the summit of this journey is within sight. We have traveled the full circumference of the ancient sky, from the Sumerian sexagesimal mathematics, whose base 60 legacy governs every clock and every angular measurement on Earth today, to the Kerala school's infinite series for the sine function, anticipated in southern India 4 centuries before Europe's calculus. We have understood that the 7 days of the week are the Babylonian planets, transmitted through 2,500 years of continuous cultural inheritance into the daily language of the modern world, and that every time a person in any European language says Wednesday or Saturday or Thursday, they are invoking, whether they know it or not, the specific divine identifications that the priest astronomers of ancient Mesopotamia assigned to the wandering lights of the night sky. We have stood at the caracol of Chichen Itza and understood that the specific orientations of its windows tracked the extreme positions of Venus with a precision that required sustained systematic observation, and that the people who built it were doing serious astronomy in a tower on the Yucatan Peninsula, while Ptolemy's geocentric model was still being refined in Alexandria. 20 facts remain. They will carry us to the end of the ancient astronomical story, to the legacy, the survival, and the specific question of what ancient astronomy means for the world that inherited it. The stars that the Babylonians tracked from their ziggurats are the same stars that shine above you tonight. They have not moved. This is explored during sleeping. Fact 81. The ancient measurement of the sun's distance, reaching for the unreachable. The measurement of the distance from the Earth to the sun, the fundamental astronomical quantity known as the astronomical unit, whose specific value anchors the entire scale of the solar system, and without whose accurate knowledge no physically meaningful model of the sun's size, the planet's orbital dimensions, or the distances to the nearest stars could be constructed, was the most ambitious measurement that ancient astronomy attempted, and the one in which the gap between ancient achievement and modern knowledge was, despite the genuine cleverness of the methods employed, the widest and the most consequential. The specific method used by Aristarchus of Samos to estimate the sun's distance, the geometric analysis of the angle between the sun and the half-illuminated moon discussed in an earlier fact, was theoretically sound, but practically limited by the extreme difficulty of determining the precise moment of half-illumination, which introduced an error of several degrees in the measured angle, whose specific consequence, through the trigonometric relationship between the angle and the distance ratio, amplified into a very large error in the final distance estimate. Aristarchus obtained a ratio of approximately 19:1 for the sun's distance relative to the moon's distance, an underestimate of the true ratio of approximately 390:1 by a factor of more than 20, but the specific direction of his reasoning, the geometric argument that the larger body must be at the center of the system, was correct despite the numerical error in its input data. Hipparchus, using the solar eclipse parallax method, discussed in the context of his lunar distance measurement, obtained a solar distance of approximately 490 Earth radii, still a large underestimate of the true value of approximately 23,500 Earth radii, and the specific failure of ancient astronomy to measure the solar distance accurately was a fundamental limitation on the development of an accurate physical model of the solar system. Persisting until the 18th century, transits of Venus provided the first reasonably accurate measurement of the astronomical unit, and the true scale of the solar system was finally revealed. Fact 82. The astronomy embedded in ancient poetry, Homer, Hesiod, and the stars. The oldest surviving works of Greek literature, the Iliad and Odyssey attributed to Homer, and the works and days and theogony of Hesiod, all composed in approximately the 8th century BCE, contain embedded within their predominantly mythological and narrative content a specific layer of astronomical and calendrical knowledge, whose particular character reflects the specific skywatching practices of the Greek world of that period, and whose careful analysis by modern scholars has revealed both the practical agricultural calendar functions served by stellar observation in archaic Greece and the specific precession-based dating evidence that allows the epoch of composition of specific passages to be estimated from the astronomical content they contain. The works and days of Hesiod, a didactic poem addressed to the poet's brother Perses, providing practical advice on agriculture, navigation, and the general conduct of life organized around a calendar of lucky and unlucky days, is the most astronomically rich of the early Greek texts. Its specific agricultural calendar, organized explicitly around the heliacal risings and settings of specific star groups, whose appearances and disappearances in the dawn or evening sky marked the appropriate times for plowing, planting, harvesting, pruning, and the various other agricultural activities that the Greek farmer needed to schedule throughout the year. The most important stellar calendar markers in Hesiod's agricultural calendar are the Pleiades, the bright star cluster in Taurus, whose specific heliacal rising in May marked the beginning of the grain harvest in the Greek agricultural tradition, and whose setting in the west before dawn in October or November marked the appropriate time for fall ploughing and the planting of winter grain, the Hyades, whose heliacal rising marked another agricultural turning point, and the appearances of Arcturus and Orion, whose specific positions in the dawn and evening sky at different times of year provided additional calendar markers for the organization of agricultural work. The specific calendar encoded in Hesiod's stellar observations was not a written calendar of the modern type, but a sky calendar, a system in which the farmer determined the time of year not from a written date, but from direct observation of the specific stars visible in the dawn or evening sky, reading the season from the sky as directly and as reliably as a modern person reads it from a calendar on a wall. Fact 83. The ancient astronomical tradition of Mesoamerica, the 260-day sacred calendar. The 260-day sacred calendar of Mesoamerica, the Tzolk'in of the Maya, the tonal Pohualli of the Aztec, the Pe of the Zapotec, and its equivalents in virtually every other pre-Columbian culture of the region, from the Olmec at the beginning of the Mesoamerican cultural tradition to the Aztec Empire at its end, is the most distinctive and most purely Mesoamerican contribution to the history of ancient timekeeping. A calendrical cycle whose specific period of 260 days corresponds to no astronomical cycle that has been identified with certainty, and whose origin has therefore been the subject of more sustained scholarly debate than almost any other specific feature of ancient Mesoamerican culture. The specific astronomical proposals for the origin of the 260-day cycle include the period of visibility of Venus as a morning star, which averages approximately 263 days, the interval between the zenith passages of the Sun at the latitude of the Mesoamerican cultural heartland of approximately 14 to 15 degrees north latitude, which is approximately 260 days, and the period of human gestation of approximately 266 days, whose specific correspondence with the 260-day cycle has led several researchers to propose a biological rather than astronomical origin for the calendar. The specific use of the 260-day calendar in Mesoamerican civilizations was primarily divinatory and ritual. Each of the 260 days was identified by a combination of one of 20-day names and one of 13-day numbers, creating a sequence of unique day identifications that cycled through all 260 combinations before repeating, and each combination was associated with specific divinatory qualities, patron deities, and auspices that determined the specific ritual activities appropriate to that day and the specific fate associated with birth on that day. The specific interlocking of the 260-day sacred calendar with the 365-day solar calendar to produce the calendar round of 52 years, the period before the same combination of sacred and solar calendar positions repeated, was the primary chronological framework for historical recording in Mesoamerican civilizations, and its specific structure reflects the profound integration of astronomical, religious, and historical consciousness that characterized Mesoamerican intellectual life from its earliest documented period. Fact 84: the ancient astronomical traditions of sub-Saharan Africa, the Dogon and the stars. The astronomical knowledge attributed to the Dogon people of Mali, the specific claims, advanced most influentially by the French anthropologists Marcel Graillou and Germain Dieterlen following their fieldwork with Dogon communities in the 1930s and 1940s, and published in their 1965 book Le Renard Pale, that certain Dogon elders possessed detailed knowledge of the star Sirius's invisible companion Sirius B, a white dwarf star whose existence was not confirmed by Western astronomy until 1862, and whose specific properties, including its orbital period around Sirius A and its extreme density, were not accurately measured until the 20th century, constitutes one of the most debated claims in the entire field of archaeoastronomy, a controversy whose specific dimensions touch on questions of anthropological methodology, the reliability of fieldwork data, the specific character of Dogon astronomical traditions, and the broader question of how astronomical knowledge is transmitted and transformed across cultural boundaries. The specific claims made by Graillou and Dieterlen were that Dogon cosmological knowledge included the existence of Sirius B, its 50-year orbital period around Sirius A, and its composition from a specific material of exceptional density, all of which corresponded accurately to the actual properties of Sirius B as measured by Western astronomy. The subsequent critical analysis of these claims by the anthropologist Walter van Beek, who conducted his own extensive fieldwork with the Dogon in the 1990s, and found no evidence that the cosmological knowledge described by Graillou was widely held in Dogon communities, or that the specific astronomical details about Sirius B were present in the traditional knowledge of the communities he studied, has led most anthropologists and archaeoastronomers to conclude that the Graillou data is unreliable, either because the information was inadvertently communicated to the Dogon informants by Graillou himself or his associates, or because it represented the specialized knowledge of one or a very few atypical individuals rather than a genuine element of the broader Dogon cosmological tradition. Fact 85: the astronomical legacy of the ancient world in modern science, the continuity of the sky. The specific legacy of ancient astronomy in the modern scientific tradition, the concrete, traceable ways in which the specific achievements of the Babylonian, Greek, Islamic, Indian, Chinese, Maya, and other ancient astronomical traditions contributed to the specific body of knowledge and the specific methodological practices of modern astronomy, is both more direct and more comprehensive than the popular history of science. With its dominant narrative of the Copernican revolution as a sharp break with the ancient tradition, typically acknowledges, and its specific character as a genuine continuity of observation, calculation, and conceptual framework across more than 2.5 millennia of astronomical practice, is one of the most important and most productive themes in the modern history of science. The most direct ancient legacy in modern astronomy is the observational record, the specific measurements of celestial positions, eclipse timings, and planetary periods accumulated by ancient astronomers whose records survive and whose data is still used by modern scientists for specific purposes that require knowledge of the sky in the distant past. The Babylonian eclipse records, preserved in the cuneiform clay tablets of the British Museum, have been used by modern astronomers to study the long-term variation in the rate of the Earth's rotation, a quantity measurable from the comparison of the predicted eclipse times, calculated from modern orbital theory, assuming a constant rotation rate, with the actual observed times recorded in the ancient records, whose specific discrepancies provide a measurement of the accumulated change in the Earth's rotation rate over the past 2,500 years of consistent observational history. The specific value of ancient eclipse records for this purpose is that no other source of information about the Earth's rotation rate before the modern instrumental period exists. The Babylonian observations are literally irreplaceable, and the specific care with which those ancient astronomers recorded the times and circumstances of each eclipse has provided modern science with a dataset of unique scientific value whose full exploitation continues to this day. Fact 86. The ancient astronomical clock of Su Song, medieval China's mechanical marvel. The astronomical clock tower constructed by the Chinese polymath Su Song in the city of Kaifeng, the capital of the Northern Song dynasty, between 1086 and 1092 CE, a structure approximately 12 meters high, housing an elaborate mechanical clockwork driven by a water-powered escapement mechanism that rotated an armillary sphere, a celestial globe, and a series of figurines that appeared at windows to mark the hours, was the most complex mechanical device constructed in the entire ancient and medieval world before the development of the European mechanical clock in the 13th and 14th centuries, and the most complete expression in any civilization before the modern period of the specific ambition to translate astronomical knowledge into mechanical form. Creating a machine that could reproduce the motions of the celestial bodies and display the time of day and the positions of the sun and moon automatically and continuously without the need for direct astronomical observation. The specific mechanism at the heart of Su Song's clock tower was the water-powered escapement, a device for converting the continuous flow of water from a reservoir into a controlled, stepwise rotation of the main drive wheel, achieving the specific function of a clock escapement, the regulation of the clock's rate to a known, constant value, through a mechanism entirely different from the Virgin foliate escapement that would be independently developed in Europe approximately 2 centuries later. The specific astronomical functions of Su Song's clock, the rotation of the armillary sphere to follow the daily motion of the celestial sphere, the rotation of the celestial globe to display the positions of the stars visible at any given moment, and the marking of the hours and watches of the day and night by the mechanical figurines, were expressions of the specific astronomical knowledge that Chinese imperial astronomy had accumulated over centuries of continuous sky observation. Translated into mechanical form by the specific genius of Su Song's engineering design and the specific resources of the Song imperial court, whose patronage made its construction possible. Fact 87. The astronomical traditions of the ancient Near East beyond Babylon, Egyptian, Hittite, and Ugaritic skis. The astronomical knowledge of the ancient Near East extended considerably beyond the Babylonian tradition, whose mathematical achievements have received the most scholarly attention, encompassing the specific skywatching practices and astronomical traditions of the Egyptian civilization of the Nile Valley, discussed in several earlier facts, and the less thoroughly documented astronomical knowledge of other ancient Near Eastern cultures, including the Hittite Empire of Bronze Age Anatolia, the Ugaritic culture of the Syrian coast, and the various Canaanite and Phoenician cultures of the Levant, whose specific astronomical traditions are partially recoverable from the texts and material culture they left behind, and whose particular character reflects the specific interaction of multiple ancient, Near Eastern skywatching traditions in a region of exceptional cultural diversity and frequent cultural contact. The Hittite Empire, the powerful Indo-European state that dominated much of Anatolia and northern Syria between approximately 1700 and 1200 BCE, and whose specific administrative records, recovered from the Royal Archive at the capital Hattusa in modern Turkey, include a corpus of astronomical and astrological texts, whose content reflects both an independent Hittite skywatching tradition and the specific influence of Babylonian omen literature that was transmitted to the Hittite court through diplomatic and scholarly contacts. Maintained an institutional astronomical tradition whose specific character combined the practical calendar functions of royal and agricultural scheduling with the omen interpretation functions of the broader ancient, Near Eastern celestial divination tradition. The specific astronomical content of the Hittite texts includes records of solar and lunar eclipses interpreted as royal omens, observations of the planets whose appearances and positions were assigned specific astrological meanings in the Babylonian tradition that the Hittite scribes had adopted and adapted, and specific festival calendars organized around celestial events whose particular structure reflects the specific integration of astronomical and religious calendrical knowledge that characterized the institutional astronomy of the ancient Near East across all its cultural variants. Fact 88. Ancient astronomical observatories of the Islamic world, the pinnacle of pre-telescopic science. The great observatories of the medieval Islamic world, the institutional astronomical establishments built and equipped with the specific patronage of Islamic rulers from the Abbasid Caliphate of Baghdad in the 9th century CE through the Timurid and Safavid courts of Central Asia and Persia in the 15th and 16th centuries, represent the highest level of organized astronomical observation achieved by any civilization before the invention of the telescope in the early 17th century, and the specific institutional model, the state-funded observatory, equipped with precision instruments and staffed by teams of professional astronomers conducting systematic long-term observational programs, whose particular development in the Islamic world provided the template for the European observatory tradition that began with Tycho Brahe's Uraniborg in Denmark in the 1570s and continues in modified form in every professional astronomical observatory operating today. The first purpose-built Islamic observatory, whose existence is documented in the historical sources, was the Shamsiyya Observatory, established near Baghdad under the Caliph al-Ma'mun in approximately 828 CE, equipped with instruments including a large meridian quadrant for measuring the altitude of the sun and stars with precision, and staffed by a team of astronomers that included the great Al-Khwarizmi, whose astronomical tables and whose development of algebra for astronomical calculation were among the most consequential scientific achievements of the Islamic Golden Age. The Observatory of Maragha, established in 1259 CE by the Mongol ruler Hulagu Khan under the direction of Nasir al-Din al-Tusi, stocked with a library of 400,000 volumes and equipped with the largest and most precise instruments then in existence, was the first observatory to function continuously for a full generation, producing the Zijai-ul-Khani astronomical tables that were used by astronomers across the Islamic world and eventually in Europe for more than a century, and providing the institutional and intellectual environment in which the Maragha revolution in astronomical theory, the critical engagement with the Ptolemaic model that developed the mathematical tools later used by Copernicus, took place. Fact 89. The ancient sky and art, cave paintings to cathedral ceilings. The specific representation of astronomical knowledge in visual art, the translation of sky observations, celestial mythology, and cosmological understanding into painted, carved, woven, and built images, whose particular character reflects both the astronomical content they encode and the specific artistic traditions within which their makers worked, constitutes one of the most pervasive and most culturally revealing dimensions of the relationship between ancient human beings and the night sky, visible in artifacts ranging from the painted cave walls of the Upper Paleolithic to the mosaic ceilings of Byzantine churches and the illuminated manuscripts of Islamic astronomical treatises. The oldest potential astronomical art in the human record is the specific cluster of dots painted on the wall of the Lascaux cave in the Dordogne region of France, dated to approximately 17,000 years ago, that has been interpreted by the researcher Michael Rappingluke as a representation of the Pleiades star cluster, the same cluster that serves as a calendar marker in Hesiod's works and days in the Babylonian star catalogues, and in the traditional astronomical knowledge of cultures on every inhabited continent. The specific identification of the Lascaux dots, as the Pleiades is based on their number, the cluster of 7 prominent dots corresponds to the 7 brightest stars of the Pleiades, as seen by a young person with good vision, and on their association in the painting with the figure of a bull, suggesting a possible representation of the constellation Taurus within which the Pleiades are located, and whose specific astronomical content would make the Lascaux painting the oldest surviving representation of a recognized constellation in the history of human art. The medieval Islamic tradition of astronomical manuscript illustration produced some of the most beautiful astronomical art in the history of any civilization. The specific constellation figures of the Arabic star catalogues, illustrated in manuscripts of exceptional artistic quality, whose particular character combined the scientific precision of the positional star data with the mythological and artistic tradition of the Hellenistic figure types. Creating images whose specific dual nature as both astronomical reference documents and works of visual art of considerable beauty has made them among the most studied and most reproduced artifacts of the Islamic artistic tradition. Fact 90. Ancient astronomical instruments in museums touching the sky's history. The surviving astronomical instruments of the ancient and medieval world, the astrolabes, quadrants, armillary spheres, sundials, and other devices whose specific function was the observation and calculation of celestial phenomena, and whose physical survival in the collections of museums and libraries across the world, provides the most direct and most intimate connection available between modern observers and the specific practice of ancient astronomy. Constitute one of the most remarkable collections of scientific artifacts in the entire history of material culture. Their particular combination of aesthetic beauty, mathematical precision, and historical significance, making them among the most treasured objects in the collections that preserve them, and among the most revealing documents of the specific astronomical knowledge and the specific craft traditions of the civilizations that produced them. The astrolabe, the most versatile and most widely produced of all pre-telescopic astronomical instruments, manufactured in large numbers by craftsmen in the Islamic world from approximately the 9th century CE onward and later in Europe from the medieval period, each one a unique combination of the specific latitude for which it was designed and the specific aesthetic and functional preferences of its maker and patron. Survives in approximately 3,000 examples in collections worldwide, ranging from functional working instruments of modest craftsmanship to elaborately decorated objects of exceptional beauty, whose specific artistic quality reflects the prestige associated with astronomical knowledge and the specific social context of the wealthy and educated patrons for whom the finest examples were made. The oldest surviving complete astrolabe, constructed in approximately 927 CE, preserved in the collection of the Museum of the History of Science in Oxford, is an object of extraordinary historical significance, a physical artifact that was used by a human being more than 1,000 years ago to tell the time from the stars, to determine the direction of Mecca for prayer, and to solve the specific spherical trigonometry problems of astronomical calculation. And whose specific brass construction, its engraved rete of star pointers, and its precisely graduated altitude circles, connects the modern observer who holds it to the specific tradition of Islamic mathematical astronomy at its most refined and most productive period. Fact 91. The ancient astronomical tradition of Mesopotamia, the mul, a pin and the shape of the sky. The mul, a pin, the Babylonian astronomical compendium, whose 2 tablets, named for the opening words that translate as the plough star, constitute the most comprehensive single document of Babylonian astronomical knowledge to survive from the ancient world and whose specific content, encompassing star catalogues organized into the 3 paths of Enlil, Anu, and E, lists of heliacal risings and settings of stars and constellations, rules for determining the dates of the solstices and equinoxes, schemes for computing the length of daylight throughout the year, and procedures for predicting the dates of the new moon, was compiled in its canonical form in approximately the 7th century BCE from earlier material that may extend back to the 12th century BCE. Providing the most complete picture available of the accumulated astronomical knowledge of Mesopotamia before the mathematical revolution of the later Babylonian period, transformed the tradition from a primarily observational and rule-based system into the fully mathematical predictive astronomy that produced the tables of the astronomical diaries and the eclipse canon, the specific content of the mul. Pin reveals a Babylonian astronomical tradition of considerable sophistication even before the mathematical revolution, one that had identified the ecliptic, the path of the sun through the fixed stars, as a distinct feature of the sky whose specific relationship with the celestial equator, the meridian and the horizon provided the geometric framework for understanding the motions of the sun, moon, and planets, the specific rules given in the mul. A pin for computing the length of daylight throughout the year, rules that assume a simple linear variation from the shortest day of winter to the longest day of summer and back, with a specific ratio of longest to shortest daylight of 2:1. Reflect both the practical accuracy of the observation that the longest summer days in Mesopotamia were approximately twice as long as the shortest winter days, and the specific mathematical simplicity of a tradition that had not yet developed the trigonometric tools needed to compute the actual variation of daylight length with greater precision. the Mul. Pin Star Catalogue, whose specific list of 36 stars and constellations, one rising heliacally each 10 days throughout the year, constitutes the earliest surviving version of the Deccan system, is the direct ancestor of both the Egyptian Deccan tradition and the Babylonian zodiacal system, making it the specific document that most clearly reveals the astronomical heritage shared by the two greatest astronomical civilizations of the ancient Near East. Fact 92. The Women of Ancient Astronomy, Hidden Figures of the Ancient Sky. The specific history of women in ancient astronomy, the recovery of the names, the achievements, and the specific contributions of women who participated in the astronomical traditions of the ancient world, in roles ranging from the purely observational to the institutional and theoretical, is a subject whose particular challenge reflects the general pattern of women's invisibility in the written records of most ancient civilizations, whose specific institutional structures concentrated literacy, institutional authority, and the keeping of records in the hands of male priestly, scribal, and scholarly classes, and whose particular consequence for the history of astronomy is that the specific contributions of women to the oldest science are recoverable only in fragments. Through the specific accidents of survival that have preserved individual names, and in some cases individual achievements, in the records of civilizations that did not systematically document women's intellectual lives. The most celebrated woman in the ancient astronomical tradition is Hypatia of Alexandria, the mathematician, astronomer, and philosopher who taught at the Neoplatonist school of Alexandria in the late 4th and early 5th centuries CE, who produced commentaries on the major mathematical and astronomical works of the ancient tradition, including Ptolemy's Almagest and Diophantus's Arithmetica, who constructed astronomical instruments including astrolabes and hydrometers for her students, and who was murdered by a Christian mob in 415 CE in circumstances that have made her one of the most written about figures in the history of ancient intellectual life, her death serving as a specific symbol, however complicated by the specific political circumstances of 5th century Alexandria, of the conflict between the classical learning tradition and the emerging Christian institutional power that would reshape the intellectual life of the Mediterranean world in the following centuries. Earlier and less celebrated women in the Babylonian astronomical tradition include the Nadatu women, the consecrated women of the temples of Babylon and Sippar, whose specific institutional roles included the maintenance of temple records, and whose literacy and institutional presence within the temple establishments that housed the professional astronomers suggests a proximity to the astronomical tradition, if not always a direct participation in it, whose specific character is recoverable only in outline from the surviving cuneiform administrative records. Fact 93. The ancient astronomy of the Pacific Islands beyond Polynesia, Micronesian and Melanesian skis. The astronomical knowledge of the Pacific Island cultures beyond the Polynesian tradition, whose navigational star compass was discussed in an earlier fact. The specific sky knowledge developed and maintained by the peoples of Micronesia and Melanesia, whose particular maritime environments and specific navigational challenges produced astronomical traditions of considerable sophistication, adapted to the specific conditions of low-latitude Pacific sailing, represents a dimension of ancient Pacific astronomy whose particular character, combining the practical demands of inter-island navigation with the cosmological and ritual frameworks of specific island cultures, has received increasing scholarly attention as the collaborative work of linguists, anthropologists, and archaeoastronomers with the living custodians of these traditions has begun to document their specific content before the continuing disruption of traditional knowledge systems by modernization makes their recovery impossible. The navigational astronomy of the Caroline Islands in Micronesia, the specific tradition of star path navigation practiced by the navigators of the Carolinian sailing canoe tradition, whose particular system of etak navigation uses a specific conceptual framework in which the navigator imagines the canoe as stationary while the islands and the stars move past, organizing the journey in terms of the sequence of stars that appear to pass overhead, is one of the most thoroughly documented traditional astronomical navigation systems in the Pacific, preserved in active practice by a small number of master navigators, and documented in detail by the anthropologist Thomas Gladwin in his 1970 book East is a Big Bird, and by subsequent researchers including David Lewis, whose comparative study of Pacific navigation traditions provided the most comprehensive survey of traditional Pacific astronomical knowledge available. The specific star path system of Carolinian navigation, in which each inter-island voyage is characterized by a specific sequence of star bearings, whose particular stars rise and set at the specific compass points needed to guide the canoe along the required course, requires the navigators to memorize the rising and setting positions of dozens of stars for dozens of different voyages. Creating a navigational knowledge system of extraordinary scope, maintained entirely in memory, and transmitted through intensive apprenticeship with master navigators, whose specific knowledge represents the accumulated navigational experience of many generations of Pacific voyaging. Fact 94. The ancient astronomical tradition of ancient Egypt, the astronomical ceiling of the tomb of Seti I. The astronomical ceiling of the tomb of Seti I, the pharaoh of the 19th dynasty, who ruled Egypt from approximately 1290 to 1279 BCE, and whose magnificent tomb in the Valley of the Kings on the west bank of the Nile at Luxor, contains some of the finest and most extensive astronomical paintings in all of ancient Egyptian art, is the most fully realized expression of the ancient Egyptian astronomical ceiling tradition. The specific tradition, whose origins in the Middle Kingdom tomb paintings developed over a millennium into the comprehensive sky maps and astronomical texts, whose particular character combines the practical astronomical information of star lists, decan sequences, and planetary positions with the religious and mythological framework of the Egyptian funerary tradition, whose specific concerns the safe passage of the deceased through the underworld and their eventual union with the eternal stars, gave the astronomical ceiling its specific ritual justification and its particular visual richness. The northern half of the Seti I astronomical ceiling depicts the circumpolar constellations in a form more fully developed and more artistically refined than any earlier Egyptian astronomical ceiling. Its specific figures including Meskhetiu, the bull's foreleg of Ursa Major, the hippopotamus goddess Taweret bearing a crocodile on her back, and the falcon-headed figure of Horus, whose specific positions in the painting encode the specific relationships between the circumpolar constellations visible from the latitude of Luxor in the New Kingdom period. The southern half of the ceiling presents the 36 decans in their sequence, accompanied by the 5 planets in their specific forms as Egyptian deities: Jupiter as Horus who bounds the 2 lands, Saturn as Horus bull of the sky, Mars as Horus the red, Mercury as Sebigu, Venus as the one who crosses. Representing the most complete surviving depiction of the Egyptian planetary tradition, and providing specific astronomical data, whose interpretation has occupied Egyptologists since the ceiling was first documented by European scholars in the 19th century. The specific astronomical content of the Seti I ceiling, the positions of the decans, the forms of the constellations, and the identifications of the planets, has been the subject of detailed comparative study with other Egyptian astronomical ceilings and with the astronomical content of the astronomical papyri, revealing both the specific evolution of the Egyptian astronomical tradition over the centuries between the earliest known astronomical ceilings and the Seti I painting, and the specific continuities that link the Seti I tradition to the much older Sumerian and Babylonian sky knowledge from which the Egyptian Deccan tradition ultimately derived. Fact 95. The ancient astronomical traditions of ancient India, the Vedanga Jyotisha. The Vedanga Jyotisha, the oldest surviving text of the Indian astronomical tradition, whose name translates approximately as the limb of the Veda concerned with the shining ones being the sun, moon, stars, and planets, is a brief astronomical treatise of approximately 36 verses in the Rigvedic version and 44 verses in the Yajurvedic version. Composed in approximately 1200 to 900 BCE, according to the astronomical evidence preserved in its specific content, and whose particular purpose, the determination of the correct times for the performance of the Vedic sacrificial rituals that constituted the primary religious obligation of the early Indian Brahminical tradition, reveals the specific institutional context within which the oldest Indian astronomical knowledge was developed and maintained. The specific astronomical content of the Vedanga Jyotisha is relatively modest by comparison with the sophisticated mathematical astronomy of the later Siddhanta period. It provides rules for computing the positions of the sun and moon in the nakshatra system, for determining the times of the solstices and equinoxes, and for calculating the specific ritual times within the 5-year yuga cycle that it uses as its primary chronological framework. But its particular historical significance is as the oldest surviving document of what would become the most mathematically sophisticated astronomical tradition in the ancient world, the tradition that would produce Aryabhata's determination of the Earth's rotation and the sidereal year, the Kerala school's infinite series for the trigonometric functions, and the computational astronomy of the great Siddhantas, whose specific achievements in mathematical modeling of the celestial motions were, at their best, competitive with the most accurate ancient astronomical models produced anywhere in the world. The specific astronomical dating of the Vedanga Jyotisha, the determination of the epoch to which its specific astronomical data corresponds, using the known precession of the equinoxes to calculate back to the period when the solstice point occupied the specific nakshatra position that the text assigns to it, yields dates ranging from approximately 1400 to 900 BCE, depending on the specific assumptions made, and provides one of the most widely discussed examples of the use of astronomical evidence for the dating of ancient Indian texts. Fact 96. The ancient astronomical tradition of Mesoamerica, the Pyramid of the Sun at Teotihuacan. The Pyramid of the Sun at Teotihuacan, the massive ceremonial structure rising approximately 66 meters above the floor of the great planned city of Teotihuacan in the Valley of Mexico, constructed in approximately the 1st and 2nd centuries CE by a civilization whose specific identity remains unknown and whose particular achievements in urban planning, monumental architecture, and long-distance trade made it the largest city in the pre-Columbian Americas at its height. With a population estimated at between 100,000 and 200,000 inhabitants, incorporates in its specific orientation and in the broader urban plan of the city a set of astronomical alignments whose particular character reflects the specific importance of solar observation in the religious and calendrical life of the Teotihuacan civilization. The specific astronomical orientation of the Pyramid of the Sun, whose western face is oriented approximately 15.5 degrees north of west, directing the sunset on two specific dates each year, approximately August 12 and April 29, to align directly with the front face of the pyramid, has been identified by the archaeoastronomer Antony Aveni as corresponding to the specific dates in the 365-day solar calendar that are separated from the summer solstice by exactly 52 days, a number of particular significance in the Mesoamerican calendrical tradition as the fundamental unit of the calendar round cycle. The broader orientation of the Teotihuacan urban grid, the entire city laid out on the same 15.5-degree offset from the cardinal directions, encompassing the major ceremonial structures, the residential compounds, and the street system, implies that the specific astronomical alignment of the Pyramid of the Sun was not an isolated feature of a single monument, but the organizing principle of the entire urban plan, suggesting that the specific astronomical knowledge encoded in the city's orientation was a foundational element of the Teotihuacan cosmological tradition, whose particular expression in urban architecture is without parallel in scale in any other ancient American city. Fact 97. The transmission of ancient astronomical knowledge, how the sky survived. The specific history of the transmission of ancient astronomical knowledge, the particular pathways through which the accumulated sky observations, mathematical techniques, and theoretical frameworks of the ancient astronomical traditions were preserved across the destruction of the civilizations that produced them and eventually incorporated into the modern scientific tradition, is one of the most consequential stories in the history of human knowledge, and one whose specific accidents of survival and specific human efforts of preservation have determined which parts of the ancient astronomical heritage are recoverable today and which have been irrecoverably lost. The most critical episode of transmission in the history of Western astronomy was the Arabic translation movement of the 8th and 9th centuries CE, the systematic effort discussed in an earlier fact, centered on the House of Wisdom in Baghdad, to render the major works of Greek science into Arabic, ensuring the survival of texts that would otherwise have been lost entirely to the disintegration of the Byzantine Empire and the general disruption of the late ancient Mediterranean world. The specific texts whose survival we owe to the Arabic translation movement include not only Ptolemy's Almagest, the foundational text of mathematical astronomy, whose Arabic transmission to Europe through the 12th century Latin translations of Gerard of Cremona made the Ptolemaic tradition available to the medieval European universities that would produce the scholars who eventually replaced it, but the complete works of Euclid, Archimedes, Apollonius, and numerous other Greek mathematical authors whose particular texts were preserved in Arabic manuscripts when the Greek originals were lost. The specific human beings most responsible for this transmission, the translators, scholars, and patrons whose particular efforts preserved the ancient astronomical heritage, include figures of remarkable individual dedication. Hunayn ibn Ishaq, the Nestorian Christian physician who translated virtually the entire corpus of Greek medical and scientific writing into Syriac and Arabic in the 9th century CE. Gerard of Cremona, the Italian scholar who spent much of his life in Toledo, translating from Arabic into Latin, producing more than 80 translations including the Almagest, and the countless unnamed scribes whose particular labor of copying and recopying ancient manuscripts in Arabic, Greek, and Latin across centuries of political disruption, ensured the physical survival of the texts on which the entire subsequent tradition of Western science depended. Fact 98. The ancient astronomical traditions of the ancient world. What was lost? The specific scale of the loss of ancient astronomical knowledge, the extent to which the accumulated sky observations, mathematical techniques, theoretical frameworks, and institutional practices of the ancient astronomical traditions have been irreversibly lost through the physical destruction of texts, the collapse of the civilizations that maintained them, and the specific accidents of preservation that have determined which small fraction of the ancient written record has survived to the present, is impossible to know with precision, but the specific evidence that survives, the tantalizing references to lost works in the surviving texts, the specific gaps in the observational record, the existence of results whose derivation has not been preserved, suggests that what we know of ancient astronomy is a small and not necessarily representative fraction of what was actually known, and that the specific achievements of the ancient astronomical traditions may have been considerably more extensive and more sophisticated than the surviving record allows us to establish. The most complete single act of astronomical knowledge destruction in the ancient world was the burning of the Library of Alexandria, or rather the series of destructions and losses that progressively diminished what was once the largest and most comprehensive collection of ancient learning ever assembled in a single institution, beginning with Julius Caesar's accidental burning of books in the harbour in 48 BCE, continuing with the partial destruction under the Roman Emperor Aurelian in 270 CE, and concluding with the gradual dispersal and loss of the remaining collections in the late antique period. The specific astronomical works known from ancient references, but no longer extant, include the complete observational records of Hipparchus, whose specific star catalogue, eclipse observations, and planetary measurements are known only through Ptolemy's citations, not through any surviving original, the complete astronomical writings of Apollonius of Perga, whose specific contributions to the mathematical theory of planetary motion were fundamental but are recoverable only from subsequent references, and the entire pre-Ptolemaic tradition of Greek mathematical astronomy, whose specific achievements, visible in outline through the works that Ptolemy superseded, can never be fully reconstructed from the surviving evidence. Fact 99. What ancient astronomy gave us: a final reckoning. The specific balance sheet of what ancient astronomy contributed to the human civilization that inherited it, the accounting of the practical gifts, the mathematical achievements, the cosmological frameworks, and the specific habits of mind that the oldest science bequeathed to every culture and every epoch that came after, is a reckoning of extraordinary scope and extraordinary consequence, encompassing contributions so fundamental to the structure of modern life that their ancient astronomical origin has become entirely invisible, dissolved into the taken-for-granted infrastructure of a civilization that has forgotten, in the way that all civilizations eventually forget, how much of what it possesses it did not make for itself. The most intimate and most pervasive of the ancient astronomical legacies is the structure of time itself, the specific division of the day into 24 hours, the week into 7 days, the year into 12 months, the circle into 360 degrees, a framework so deeply embedded in every aspect of modern life that its specific astronomical origins in the Babylonian sexagesimal mathematics of the 3rd millennium BCE, the Egyptian civil calendar of the ancient Nile Valley, and the Greek geometrical tradition that synthesized them into the specific forms we use today, are essentially invisible to the billions of people whose daily lives are entirely organized by these inherited structures. The mathematical legacy of ancient astronomy is equally pervasive. The trigonometric functions whose invention was motivated by the specific computational needs of ancient astronomers, the algebraic notation developed by Islamic mathematicians working on astronomical problems, the specific numerical techniques of ancient Indian astronomers that underlie the computational mathematics of the modern world. All of these are products of the specific intellectual effort to understand the sky that ancient civilizations sustained across thousands of years and dozens of generations of dedicated practitioners. Beyond the practical and the mathematical, ancient astronomy gave to every civilization that practiced it something less tangible, but no less real, the specific experience of understanding, even partially, the structure of the cosmos in which human beings find themselves, the particular satisfaction of knowing that the lights moving across the night sky are not random or arbitrary, but lawful and predictable and knowable, that the universe has a structure that the human mind can penetrate. An experience whose specific importance for the confidence and the orientation of the cultures that achieved it was and remains incalculable. Fact 100. The stars above. What remains when everything else has gone? Close your eyes, breathe slowly. The stars above you tonight are the same stars that the first Babylonian astronomer recorded on a clay tablet 4,000 years ago. They are the same stars that Hipparchus measured from the island of Rhodes, that Al-Battani observed from his tower on the Euphrates, that the Polynesian navigator used to find his way across 10,000 kilometers of open ocean without compass or chart. They are the same stars that a Neolithic farmer in the Boyne Valley of Ireland aligned a passage tomb to greet at the winter solstice, so that the light would come in every year at that specific moment and fill the chamber with gold, and the community would know that the darkest time had passed. They are the same stars that an Aboriginal Australian elder read as a dark emu settling in the Milky Way and understood that the time had come to go and find the eggs. Nothing about the night sky that any human being has ever looked at is lost. The photons that fell on the eyes of the Babylonian astronomer standing on his ziggurat, the photons that fell on Hypatia in the last years of the ancient world, the photons that guided the canoes of the Pacific, those specific photons are gone, absorbed into the specific retinas of the specific human beings who received them, long since dissipated into biological heat. But the source of those photons, the stars themselves, is unchanged. Aldebaran is still in Taurus. Orion still rises in the east on winter evenings. The Pleiades still set in the west in spring. The Milky Way still arcs from horizon to horizon on a dark, clear night, its dark clouds still forming the emu and the jaguar and the serpent that the peoples of the southern hemisphere have read in it for 65,000 years. Every civilization that has ever existed looked up at this sky and found in it the same fundamental order, the same rising and setting, the same cyclical return of the same stars to the same positions in the same seasons, the same planetary wanderers tracing the same slow paths against the same background of fixed stars. And in that order, in the specific legibility of a universe that could be read by patient human attention, every civilization found something that was not merely useful, but essential, confirmation that the world in which they lived was governed by laws that exceeded human power, but did not exceed human understanding, that the darkness above them was not chaos but pattern, that the night sky was not a ceiling but a window. You are lying in that darkness now. The same sky is above you. The same stars are there, beyond the light pollution and the clouds and the ceiling of whatever room you are in, patient, regular, ancient beyond any human scale of age, and entirely indifferent to the passage of the civilizations that have looked up at them and found in their specific patterns the first, the oldest, and the most enduring evidence that the universe is knowable. This is explored during sleeping,